Terraforming, the process of transforming a planet's environment to make it habitable for humans, is perhaps the most ambitious engineering project conceivable. At first glance, it seems like a purely technological challenge: adjust the atmosphere, warm the surface, introduce liquid water. But the deeper you look, the more apparent it becomes that terraforming is not just a scientific endeavor, it is a civilizational one. Its success depends entirely on whether humanity can first achieve something it has not yet managed on its home planet: a truly sustainable society. The dependency chain. Terraforming a planet like Mars would take anywhere from decades to millennia, depending on the approach. That timescale alone reveals the first and most fundamental sustainability requirement: continuity. No single generation, government, corporation, or civilization can complete a terraforming project. It must be carried forward across hundreds of generations, which means the institutions, knowledge systems, and resource bases that support it must themselves be indefinitely sustainable. This creates a profound dependency chain. Terraforming requires advanced technology. Advanced technology requires a functioning industrial civilization. A functioning industrial civilization requires stable energy, food, water, governance, and social cohesion. Each of these, in turn, requires sustainability in its own domain. Pull any link from the chain and the entire project collapses, not just pauses, but potentially reverses irreversibly. Energy sustainability. Every stage of terraforming is energy intensive to a staggering degree. Heating a planet, synthesizing greenhouse gases, driving chemical reactions across a planetary surface, powering the spacecraft and habitats that support the effort. All of this demands energy at scales that dwarf current human consumption. This energy cannot come from finite fossil fuel reserves. Even if Earth's coal and oil were burned entirely in service of a terraforming project, they would be exhausted long before the work was complete, leaving behind a degraded home planet and a half-finished new one. Only renewable energy systems, solar, wind, nuclear fusion, and others not yet developed, can provide the sustained, scalable, and indefinitely available power that terraforming demands. Moreover, the energy infrastructure supporting terraforming must itself be resilient and self-replicating. Solar panels degrade, wind turbines wear out, nuclear reactors require fuel and maintenance. A civilization capable of sustaining a centuries-long terraforming effort must have mastered the full cycle of energy technology, manufacture, deployment, maintenance, recycling, and upgrade, all powered by the energy system itself. This is, in essence, a completely closed and sustainable energy economy. Materials and industrial sustainability. Terraforming consumes materials at a planetary scale. The chemicals, metals, polymers, biological organisms, and mechanical systems required must be produced continuously and reliably. This demands a fully circular industrial economy, one in which waste from one process feeds the next, in which nothing is lost to landfill or pollution, and in which the extraction of raw materials is matched by the recovery and reuse of existing ones. If Earth's industrial systems continue to deplete finite mineral reserves, contaminate ecosystems, and generate irrecoverable waste, then the material foundation of terraforming will erode over time. The rare earth elements needed for advanced electronics, the phosphorus needed for agriculture, the fresh water needed for manufacturing, all are finite or fragile resources that require careful stewardship. A civilization that exhausts its resource base on Earth cannot simultaneously terraform another planet. In situ resource utilization, using the materials of the target planet itself, partially addresses this, but it requires extraordinarily sophisticated manufacturing capability bootstrapped from Earth. That capability must be built and sustained here first. Food and agricultural sustainability. The crews, scientists, engineers, and administrators supporting a terraforming project must eat. At the early stages, food may be grown in pressurized habitats on the target planet, but the broader civilization sustaining the project, the billions of people on Earth whose labor, taxes, and political support make it possible, must also be fed, stably and equitably, across the entire duration. A civilization facing food insecurity, driven by soil degradation, aquifer depletion, climate disruption, or collapsing biodiversity, cannot maintain the political will or economic capacity to pursue a generations-long extraterrestrial project. Agricultural sustainability, regenerative soil management, water-efficient farming, crop diversity, equitable food distribution, is therefore not peripheral to terraforming. It is foundational to it. There is also a direct technical connection. The ecological knowledge gained from sustaining complex life support systems in agriculture directly informs the biological terraforming of another planet. Closed-loop life support systems, soil microbiome engineering, and synthetic ecology all draw on the same science as sustainable agriculture. Political and institutional sustainability. Terraforming is the only engineering project in history that would require uninterrupted institutional commitment across multiple centuries. No democracy has a planning horizon beyond a few election cycles. No corporation plans beyond a few decades. No empire in history has lasted long enough to see a terraforming project through from start to finish. This means that sustainable governance, institutions capable of making and keeping long-term commitments, of surviving political upheaval, of distributing benefits equitably enough to maintain public legitimacy, is a prerequisite for for terraforming. A civilization riven by inequality, nationalism, short-termism, and institutional decay cannot coordinate a planetary engineering project. The sustainability of democratic institutions, international cooperation frameworks, scientific bodies, and legal systems is therefore directly relevant. Treaties governing the use of space, agreements on burden sharing for the cost of terraforming, mechanisms for resolving disputes over who benefits and who decides, all of these require political sustainability as their foundation. Economic sustainability. The cost of terraforming, by any credible estimate, would be measured in the tens or hundreds of trillions of dollars over the course of the project. Sustaining that level of investment across centuries requires an economy that is itself growing, stable, and broadly shared. An economy hollowed out by inequality, environmental degradation, or resource depletion cannot generate the surplus needed to fund terraforming. The economic sustainability of Earth, maintaining productive capacity, investing in education and innovation, managing debt and financial instability, and ensuring that enough people have enough prosperity to support ambitious long-term projects, is a direct prerequisite. Furthermore, the economic logic of terraforming only holds if Earth itself remains valuable and inhabited. A civilization that has destroyed its own planet in pursuit of a new one has not achieved sustainability, it has merely relocated collapse. Ecological and biodiversity sustainability. One of the most technically demanding aspects of terraforming is biological, seeding a lifeless planet with a self-sustaining ecosystem. This requires an intimate understanding of how ecosystems function, how species interact, how soil microbiomes build fertility, how nutrient cycles close, and how ecological resilience is achieved and maintained. All of that knowledge comes from studying and preserving life on Earth. A civilization that allows mass extinction to continue, losing thousands of species in the ecological functions they perform, is simultaneously destroying the library from which terraforming must draw. Every species lost is a potential tool, a genetic resource, a model organism, or an ecological keystone that might have been critical to building a new biosphere. Biodiversity conservation is therefore not merely an ethical obligation. For a civilization serious about terraforming, it is a practical necessity. The sustainability of Earth's biosphere is the research and development foundation of any future biosphere. Technological sustainability and knowledge continuity. Terraforming requires technologies that do not yet exist, advanced atmospheric chemistry, genetic engineering of extremophile organisms, large-scale orbital manufacturing, autonomous robotic systems capable of operating for decades without human oversight. Developing these technologies requires sustained investment in basic science and engineering over generations. Scientific institutions, universities, research funding bodies, and the cultural norms that make science possible, openness, skepticism, collaboration, reproducibility, must all be maintained and protected. A society that deafens science, suppresses expertise, or allows scientific knowledge to be lost faces a technological regression incompatible with terraforming's demands. Knowledge continuity, the ability to pass accumulated understanding reliably from one generation to the next, is itself a form of sustainability. The loss of institutional knowledge, whether through war, political suppression, or cultural collapse, could set a terraforming project back by centuries. The recursive insight. Here is the deepest insight that emerges from this analysis. Terraforming cannot be a substitute for sustainability on Earth, it can only be an extension of it. The skills, habits, institutions, and technologies required to terraform another planet are exactly the same ones required to sustain civilization on this one. A circular economy, renewable energy, regenerative agriculture, stable governance, equitable prosperity, and a living biosphere are not just preparations for terraforming, they are terraforming, applied at home. In a profound sense, humanity is already engaged in a terraforming project, the inadvertent one of destabilizing Earth's climate and ecosystems. The deliberate, constructive version, the one that builds rather than degrades, demands that we first demonstrate mastery of the same planetary scale systems we are currently mismanaging. Terraforming Mars, or any other world, begins not with rockets or atmospheric processors, but with the decision to build a civilization on Earth that can last. Everything else follows from that. How can we increase sustainability at all levels to be able to terraform other planets? This is one of the most expansive questions humanity can ask, because answering it seriously means redesigning nearly every system we have. This is one of the most expansive questions humanity can ask, because answering it seriously means redesigning nearly every system we have. Here is a comprehensive exploration, level by level. The individual level. Sustainability begins with how billions of individuals live, consume, and choose. While systemic change matters more than personal behavior in isolation, culture is made of individuals, and individual norms shape political will, consumption and lifestyle. The average person in a wealthy nation consumes resources at a rate several times what Earth can sustainably provide, shifting toward lower meat diets, reduced fast fashion, longer product lifespans, and smaller living spaces are not sacrifices, they are recalibrations towards sufficiency. The key insight is that well-being and consumption are not the same thing. Beyond a certain threshold of material comfort, additional consumption adds little to human happiness while imposing enormous ecological costs. Education and scientific literacy. A civilization capable of terraforming must be a civilization that broadly understands science, systems thinking, and long-term consequences. Investing in science education, critical thinking, and ecological literacy from childhood produces citizens capable of making informed decisions and supporting ambitious long-term projects. Scientific illiteracy is not just an individual limitation, it is a civilizational vulnerability. Civic participation. Individuals who vote, advocate, organize, and hold institutions accountable create the political conditions in which sustainability policies can be enacted and maintained. Apathy and disengagement are forms of unsustainability in the political realm. The connection between an engaged citizenry and a civilization capable of multi-century commitments is direct. The community and city level. Cities house more than half of humanity and consume roughly 75% of global energy. They are also the most efficient human settlement pattern. Dense urbanism dramatically reduces per capita energy use, land consumption, and transportation emissions compared to sprawl. Urban design. Cities designed around walking, cycling, and public transit rather than private automobiles are more sustainable, healthier, and more socially cohesive. Mixed-use zoning, green space integration, and neighborhood-scale food production reduce the ecological footprint of urban life while improving its quality. The sustainable city is not a sacrifice, it is generally a more pleasant place to live. Local food systems. Urban agriculture, community gardens, rooftop farming, and short supply chains reduce the energy and emissions embedded in food transport while building community resilience. Cities that can partially feed themselves are more robust to supply chain disruptions, exactly the kind of resilience a civilization maintaining an off-world project requires. Circular material flows. Communities can develop local recycling and composting infrastructure, repair economies, tool libraries, and sharing systems that dramatically reduce waste. The neighborhood scale is often where circular economy principles are most practically implemented, where the flows of materials are small enough to manage and the social trust is high enough to cooperate. Resilient infrastructure. Decentralized energy systems, rooftop solar, community batteries, microgrids, make communities resilient to grid failures. Distributed water harvesting and treatment reduce dependence on centralized systems vulnerable to disruption. Building this resilience at the community level is essential for a civilization that must maintain continuity across centuries. The national level. Nations are still the primary units of policy, law, taxation, and major infrastructure investment. National level decisions set the rules within which businesses and individuals operate. Energy transition. The single most important national sustainability action is the rapid, complete transition from fossil fuels to renewable energy. This means massive investment in solar, wind, geothermal, and next-generation nuclear, the build-out of transmission infrastructure and storage, the electrification of heating, transport, and industry, and the retirement of fossil fuel infrastructure on an accelerated timeline. No other national action has comparable leverage on long-term civilizational sustainability. Carbon pricing. Putting a meaningful price on carbon emissions, through a carbon tax or cap-and-trade system, is the most economically efficient way to drive decarbonization across the entire economy simultaneously. It makes fossil fuels bear their true cost, makes clean alternatives more competitive, and generates revenue that can be invested in the transition or returned to citizens. Circular economy legislation. National governments can mandate extended producer responsibility, set recycled content requirements, ban single-use plastics, require design for repairability, and establish landfill taxes that make linear production economically uncompetitive. The European Union Circular Economy Action Plan is the most comprehensive example to date, but it must be replicated and exceeded globally. Education and research investment. Sustained national investment in basic scientific research, universities, and technical education is essential. The technologies needed for terraforming, fusion energy, closed-loop life support, atmospheric chemistry at scale, synthetic biology, do not yet exist. Developing them requires decades of patient, publicly funded research. Nations that defund science are withdrawing from the terraforming project whether they know it or not. Long-term institutional design. Democratic systems tend toward short planning horizons. Nations can counteract this by creating independent long-term planning institutions, bodies insulated from electoral cycles that monitor planetary boundaries, assess civilizational risks, and recommend policy with a century-scale perspective. Finland's Committee for the Future and Wales's Future Generations Commissioner are early experiments in this direction. The industrial and corporate level. Industry is responsible for the majority of resource extraction, energy consumption, and waste generation. Transforming industry is therefore the core challenge of sustainability. Decarbonizing hard-to-abate sectors. Steel, cement, chemicals, shipping, and aviation account for a large fraction of industrial emissions and are particularly difficult to decarbonize. Green hydrogen, produced by electrolysis using renewable electricity, is a promising route for steel and chemical production. Carbon capture and utilization can address residual emissions. Alternative cement chemistries can dramatically reduce the carbon intensity of construction. Each of these requires sustained industrial R&D and policy support. Fully circular manufacturing industry must move from linear, extract, make, dispose, to circular, design, use, recover, reuse, models across all sectors. This means designing products for disassembly and material recovery, building take-back and remanufacturing systems, and treating waste streams as feedstocks. The industrial symbiosis model, where clusters of companies exchange waste streams, must become the norm rather than the exception. Sustainable supply chains. Global supply chains are extraordinarily complex and often obscure environmental and social harms deep in the chain. Companies must take responsibility for the full life cycle of their products, from raw material extraction through manufacturing, transport, use, and end-of-life recovery. Transparency tools, supply chain mapping, and traceability technologies make this increasingly possible. Corporate governance and time horizons. Publicly traded corporations are structurally biased toward short-term results. Reforming corporate governance, through longer-term executive compensation structures, stakeholder governance models, benefit corporation legal frameworks, and patient capital from long-term investors, can extend corporate planning horizons toward the timescales that sustainability and terraforming demand. The agricultural and food system level. Food production is the human activity with the largest land and water footprint, the largest driver of biodiversity loss, and a significant contributor to greenhouse gas emissions. Transforming it is essential. Regenerative agriculture. Moving beyond the industrial monoculture model toward regenerative practices, cover cropping, no-till farming, agroforestry, rotational grazing, and soil microbiome management, rebuilds soil health, sequesters carbon, reduces water use, and increases resilience to climate disruption. Healthy soils are not just an agricultural resource, they are the foundation of terrestrial ecosystems and the model for any soil-building effort on another planet. Dietary transition. Shifting global diets toward more plant-based foods, not necessarily fully vegan, but significantly reduced in meat, especially beef, is one of the highest leverage interventions available. Animal agriculture, particularly ruminant livestock, consumes enormous land and water resources and generates substantial methane emissions. A world that eats differently could free up vast areas of land for ecosystem restoration while dramatically reducing agricultural emissions. Precision fermentation and alternative proteins. Technologies like precision fermentation, cultivated meat, and plant-based protein engineering can produce nutritious food with a fraction of the land, water, and emissions of conventional animal agriculture. These technologies also have direct relevance to terraforming. Feeding a crew on Mars or producing food in a closed habitat requires exactly the kind of compact, efficient, resource-minimal food production that these approaches represent. Reducing food waste. Cutting the one-third of food that is currently lost or wasted, through better cold chain infrastructure, smarter retail and consumer practices, and valorization of food byproducts, effectively increases the productive capacity of the food system without expanding its footprint. The ecological and biodiversity level. Earth's biosphere is not just a backdrop to human civilization, it is the life support system on which everything depends, and the library from which terraforming must be written. Ecosystem restoration. Restoring degraded forests, wetlands, grasslands, and marine ecosystems serves multiple functions simultaneously. It sequesters carbon, protects biodiversity, regulates water cycles, and builds the ecological knowledge base needed for terraforming. The UN Decade on Ecosystem Restoration represents a growing global commitment, but the scale and ambition need to increase dramatically. Biodiversity conservation. Halting and reversing the sixth mass extinction requires protecting remaining wild habitats, creating wildlife corridors, managing invasive species, reducing pollution, and addressing the root drivers of habitat loss. Every species preserved is a potential tool for building a new biosphere. The genetic diversity of life on Earth is irreplaceable, and its loss is permanent. Synthetic ecology research. Understanding how ecosystems assemble, stabilize, and recover from disturbance is directly relevant to the biological phase of terraforming. Research into succession ecology, keystone species, trophic cascades, and microbiome dynamics on Earth informs every aspect of designing a new biosphere from scratch. The technological level. Many of the technologies needed for long-term sustainability and terraforming do not yet exist at commercial scale. Developing them requires sustained, coordinated investment. Fusion energy. If achieved at commercial scale, fusion energy would provide effectively unlimited, clean, safe power, transforming the energy constraint from a bottleneck into a solved problem. ITER and several private ventures are making genuine progress, though commercial fusion remains years to decades away. Advanced nuclear fission. Next-generation fission reactors, small modular reactors, thorium reactors, molten salt designs, offer safer, more flexible, and potentially more sustainable nuclear power that can complement renewables and provide baseload power in any environment, including off-world habitats. Closed-loop life support. The International Space Station's life support systems close some loops, recycling water and oxygen, but remain dependent on resupply. Fully closed life support systems, capable of recycling all materials indefinitely using only energy inputs, are essential for long-duration space habitation and represent the ultimate expression of circular economy principles. Synthetic biology engineering organisms to perform specific ecological functions, fixing nitrogen, building soil structure, producing oxygen, degrading pollutants, synthesizing materials, is a technology with enormous implications for both Earth's sustainability and planetary terraforming. The biological terraforming of Mars would rely heavily on engineered extremophile organisms capable of surviving and gradually modifying a hostile environment. Artificial intelligence and systems modeling managing the complexity of a global sustainable economy, or a terraforming project, requires computational tools capable of modeling and optimizing systems of extraordinary complexity. AI applied to materials discovery, energy grid management, ecological monitoring, and long-term planetary modeling accelerates progress across all sustainability domains. The global governance level. No nation can achieve sustainability alone, and no nation can terraform a planet alone. Global coordination is essential at both scales. Strengthening international institutions. The United Nations, international scientific bodies, treaty organizations, and multilateral development banks must be strengthened, reformed, and better funded. The institutions capable of coordinating a global sustainability transition are the same ones that would need to coordinate a terraforming project, and they must be built and tested on Earth first. Global carbon markets and finance. A functioning global carbon market, combined with substantial financial flows from wealthy to developing nations for clean energy transition and adaptation, is essential for bringing the entire world into a sustainable trajectory. Climate finance is not charity, it is investment in the global stability that long-term civilizational projects require. Space governance. The Outer Space Treaty of 1967 provides a thin legal framework for space activity. As the prospect of planetary modification becomes more real, far more robust international governance will be needed. Agreements on who has the right to terraform, how benefits and costs are shared, what ecological protections, if any, apply to other worlds, and how disputes are resolved. Building this governance framework requires the same multilateral cooperation muscles that global sustainability demands. Knowledge commons. The scientific and technical knowledge needed for sustainability and terraforming must be treated as a global commons, openly shared, collectively built, and universally accessible. Intellectual property regimes that lock up critical technologies behind paywalls slow the global transition and concentrate the benefits of innovation inequitably. The unifying principle. Across every level, individual, community, national, industrial, agricultural, ecological, technological, and global, the same principle emerges. Sustainability is not a constraint on human ambition. It is the prerequisite for it. A civilization that cannot sustain its soils cannot feed a terraforming crew. A civilization that cannot sustain its energy systems cannot power a planetary engineering project. A civilization that cannot sustain its institutions cannot maintain a centuries-long commitment. A civilization that cannot sustain its biosphere cannot design a new one. Every act of genuine sustainability, every solar panel installed, every ecosystem restored, every circular supply chain built, every long-term institution strengthened, is simultaneously an act of preparation for the most ambitious project our species has ever conceived. The path to other worlds runs directly through the stewardship of this one. There is no shortcut, and no alternative starting point. The question of how to terraform other planets, and the question of how to sustain life on Earth turn out, on close examination, to be the same question. Answering one is answering the other. How can we terraform other planets by increasing sustainability of our society and the global environment? This is the ultimate convergence question, where planetary stewardship and interplanetary ambition meet. The answer reveals something profound. Every genuine sustainability advance on Earth is simultaneously a step toward terraforming other worlds. Here is a comprehensive exploration of exactly how. The foundational logic. Terraforming is not a project that begins when a rocket launches. It begins the moment a civilization commits to mastering planetary systems, atmosphere, hydrology, soil, energy, ecology, at scale. Every technology, institution, and body of knowledge developed in the pursuit of sustainability on Earth is directly transferable to the modification of another planet. The relationship runs in both directions. Sustainability without the long-term vision of expansion becomes mere survival management. Terraforming without the foundation of sustainability is fantasy built on a collapsing base. Together, they form a coherent civilizational project. Master your home world, then extend life beyond it. Energy mastery. From renewable Earth to power terraforming. On Earth, the transition to fully renewable energy, solar, wind, geothermal, tidal, and advanced nuclear, is the single most transformative sustainability step available. It ends the extraction and burning of finite carbon reserves, stabilizes the climate, and demonstrates that a technological civilization can power itself indefinitely from ambient flows of energy rather than depleting stocks. The terraforming connection. Every terraforming scenario requires energy at civilizational scale, sustained across centuries, heating Mars to habitable temperatures, driving atmospheric chemistry, powering manufacturing and life support, propelling supply emissions. All of this demands energy infrastructure that is self-sustaining, self-replicating, and renewable. The solar farms, fusion reactors, and advanced nuclear systems developed for Earth's sustainable energy transition are the direct prototypes for the power systems that will run a terraforming project. Specifically, small modular nuclear reactors developed for remote Earth communities translate directly to planetary surface power stations. Space-based solar power, collecting sunlight in orbit and beaming it to the surface, tested first for Earth applications, could serve as a primary energy source for a planet like Mars that receives less solar radiation. Fusion energy, if achieved on Earth, would essentially solve the energy constraint for terraforming entirely. The feedback loop. A fully renewable Earth civilization generates no carbon debt, has no energy scarcity, and can direct its surplus energy capacity toward the enormous power demands of space industrialization and terraforming without compromising the home planet. Atmospheric science. From climate repair to atmosphere building. On Earth, humanity is currently engaged in the largest unintentional atmospheric modification experiment in history, and is now developing the tools to understand and eventually reverse it. Carbon capture technologies, atmospheric modeling, greenhouse gas monitoring, stratospheric aerosol research, and ocean chemistry science are all advancing rapidly in response to the climate crisis. The terraforming connection. Mars has an atmosphere roughly 100 times thinner than Earth's, composed almost entirely of CO2, with surface temperatures averaging -60 degrees Celsius. Terraforming Mars requires thickening and warming its atmosphere, the precise inverse of what Earth currently needs to do. The science of atmospheric modification developed in the context of Earth's climate crisis is directly applicable. Techniques under study for Earth, releasing specific greenhouse gases, managing aerosols, altering surface albedo, are early versions of what would be deployed at planetary scale on Mars. The atmospheric chemistry models built to predict Earth's climate decades into the future are the same models that would be used to plan and monitor a Martian atmospheric transformation over centuries. Every climate scientist trained, every satellite monitoring system built, every carbon cycle model refined is simultaneously advancing terraforming science. Direct air capture technology, machines that pull CO2 from Earth's atmosphere to combat climate change, run in reverse, become machines that produce and inject greenhouse gases into it and planetary atmosphere to warm it. The engineering problems are related, and progress on one advances the other. Closed-loop material systems, from circular economy to closed habitats. On Earth, the circular economy, in which all materials cycle continuously through use, recovery, and reuse, with no net waste, is the sustainability ideal for industrial civilization. Achieving it requires advances in materials science, process engineering, product design, logistics, and chemistry that collectively eliminate the concept of waste. The terraforming connection, a habitat on Mars, or a crew on a generation ship, cannot afford waste in any form. Every atom of oxygen, every molecule of water, every gram of food must cycle through the system indefinitely. The closed-loop life support systems needed for space habitation are the circular economy taken to its logical extreme, a completely closed material cycle powered only by energy. The International Space Station currently recycles about 90% of its water and regenerates oxygen from CO2. Achieving 100% closure, for water, air, food, and all materials, is the engineering challenge that directly parallels the circular economy challenge on Earth. Every advance in industrial recycling, biological nutrient cycling, water purification, and waste valorization on Earth contributes directly to closing the loops in space. In situ resource utilization, using Martian soil, rock, and atmosphere to produce building materials, oxygen, water, and fuel, requires exactly the kind of creative material science and process engineering that the circular economy demands. Researchers working on turning Martian perchlorate-rich regolith into construction material are solving problems structurally identical to those of turning industrial waste into useful products on Earth. Synthetic biology and ecology, from biosphere repair to biosphere construction. On Earth, the restoration of degraded ecosystems, the conservation of biodiversity, and the emerging field of synthetic biology are building humanity's capacity to understand, design, and manage living systems. Rewilding projects, soil microbiome research, ecological succession studies, and the genetic engineering of organisms for specific environmental functions are all advancing this capacity. The terraforming connection, the biological phase of terraforming, seeding a lifeless planet with life that gradually modifies the environment toward habitability, is the most complex and least understood aspect of the entire project. It requires organisms capable of surviving extreme cold, radiation, low pressure, and toxic chemistry, while performing useful ecological functions, fixing nitrogen, building soil, producing oxygen, cycling nutrients. Every extremophile organism discovered and studied on Earth, in hydrothermal vents, Antarctic ice, acidic hot springs, deep rock formations, expands the known envelope of life and provides models for the organisms that might be engineered for Mars. Every advance in synthetic biology, the ability to design organisms with specific metabolic capabilities, is directly applicable to engineering the pioneer species that would begin biological terraforming. Ecological restoration science, understanding how pioneer species prepare an environment for successional communities, how soil builds over time, how nutrient cycles establish themselves, is the theoretical foundation of terraforming ecology. Restoring a clear-cut forest or a degraded wetland on Earth is, in miniature, the same challenge as establishing life on a barren planet. Preserving Earth's biodiversity is therefore not merely an ethical imperative, it is the preservation of the genetic and ecological library from which terraforming must be written. Every species lost is a potential tool for building a new world, gone forever. Water mastery, from hydrological restoration to planetary hydrology. On Earth, sustainable water management, aquifer recharge, watershed restoration, atmospheric water harvesting, advanced desalination, precision irrigation, and wetland conservation, is building humanity's capacity to manage water at landscape and continental scales. Reversing the degradation of the global hydrological cycle is one of the central sustainability challenges of the coming century. The terraforming connection, Mars almost certainly contains substantial water, in polar ice caps, subsurface permafrost, and possibly underground liquid reservoirs. Unlocking, distributing, and managing this water is central to any terraforming scenario. The planetary hydrological engineering needed to create rain cycles, river systems, and stable liquid water on a terraformed Mars draws directly on the hydrological science developed in the context of Earth's water crisis. Atmospheric water harvesting technologies developed for arid regions on Earth translate to water extraction from the Martian atmosphere. Desalination and water purification advances reduce the cost and energy of processing whatever water is found. Watershed management science informs how water might be cycled in an early Martian ecosystem. Every river restored, every aquifer managed sustainably, every innovative water technology deployed on Earth is simultaneously an advance in the water engineering toolkit that terraforming requires. Food system innovation, from sustainable agriculture to off-world feeding. On Earth, the transformation of the food system toward regenerative agriculture, precision fermentation, cultivated meat, vertical farming, and dramatic reduction in food waste is building both the sustainability of Earth's food supply and the technologies needed to feed people anywhere in the solar system. The terraforming connection, feeding a crew on Mars, or eventually a population on a terraforming planet, requires food production systems that are compact, efficient, closed-loop, and capable of operating in alien conditions. The vertical farms, hydroponic systems, precision fermentation reactors, and algae cultivation technologies being developed for Earth's sustainable food future are the direct ancestors of Martian food production systems. Soil building research, understanding how microbial communities, organic matter, and mineral weathering combine to create fertile soil, is directly applicable to developing agricultural capacity on a terraformed Mars, which must build its soils from sterile regolith over decades or centuries. Crop varieties engineered for drought tolerance, temperature extremes, and nutrient efficiency on Earth are the starting points for varieties engineered for Martian conditions. The reduction of food waste on Earth is itself a sustainability advance with a space analog. On Mars, food waste is simply not an option. The discipline, technology, and systems thinking developed to eliminate food waste in Earth's supply chains translates directly to the zero-waste food systems of space habitation, governance and institutions, from global cooperation to interplanetary coordination. On Earth, building the international institutions, treaties, and cooperation frameworks capable of managing global commons, the atmosphere, the oceans, biodiversity, the climate, is directly developing the governance capacity needed to manage a terraforming project. The terraforming connection, a terraforming project spanning centuries across multiple nations and eventually multiple worlds requires governance institutions of extraordinary durability, legitimacy, and effectiveness. The multilateral bodies, international scientific collaborations, and long-term treaty frameworks being built to address climate change, biodiversity loss, and ocean governance are the prototypes. The Paris Agreement, imperfect as it is, represents humanity's first serious attempt at coordinating action on a planetary scale problem across nearly every nation on Earth. The Intergovernmental Panel on Climate Change represents an unprecedented model for translating scientific consensus into policy guidance at global scale. The Convention on Biological Diversity represents an attempt to govern a global commons. Each of these institutions, strengthened and made more effective, becomes the template for the governance of a terraforming project and eventually of multiple inhabited worlds. Space law itself, the Outer Space Treaty, the Artemis Accords, emerging frameworks for resource utilization and planetary protection, must evolve rapidly. The legal and diplomatic work of establishing clear, fair, and enforceable rules for space activity is a prerequisite for any cooperative terraforming effort. This work proceeds in parallel with, and draws heavily on, the experience of governing global environmental commons on Earth, economic systems, from sustainable economics to interplanetary investment. On Earth, transitioning from an economy that treats natural capital as free and infinite to one that prices environmental goods and services correctly, invests in long-term assets, and distributes benefits broadly enough to maintain social legitimacy is the economic dimension of sustainability. It requires carbon pricing, natural capital accounting, long-term investment frameworks, and economic models that treat human well-being rather than GDP growth as the measure of success. The terraforming connection. A terraforming project is the longest-term investment in human history. Its costs are borne by present generations, its benefits accrue to generations centuries in the future. No conventional economic framework can justify this investment on standard return on investment terms. Only an economic system already oriented toward long-term thinking, intergenerational equity, and the valuation of assets that pay off over centuries can sustain the financial commitment terraforming requires. The economic institutions being developed for sustainable finance, green bonds, long-term sovereign wealth funds, natural capital accounting, intergenerational equity frameworks, are the prototypes for the economic architecture of a terraforming fund. A civilization that has learned to invest in 50-year infrastructure, 100-year ecosystem restoration, and 200-year climate stabilization is a civilization capable of investing in a 500-year terraforming project. The integrated vision. Bring all of these threads together and a coherent picture emerges. Increasing sustainability at every level of society, and the global environment does not merely prepare humanity for terraforming, it is the first phase of terraforming, conducted on the only planet where we already know life can thrive. The sequence is clear. Phase 1, stabilize Earth, transition to renewable energy, stabilize the climate, restore ecosystems, establish circular material flows, and build durable global governance. This is the work of the next 50 to 100 years. Phase 2, master planetary systems, develop the full toolkit of atmospheric science, synthetic ecology, hydrological engineering, closed-loop life support, and long-duration space habitation through missions to the Moon and Mars. This overlaps with Phase 1 and extends 50 to 200 years into the future. Phase 3, begin terraforming, deploy the technologies, organisms, and systems developed in Phases 1 and 2 to begin the deliberate modification of a target planet. This is work that begins in earnest perhaps 100 to 200 years from now, and unfolds over centuries to millennia. Each phase enables the next. None can be skipped. In the first phase, the sustainability transition on Earth is not a distraction from the grand vision of becoming a multiplanetary species. It is the indispensable foundation without which no subsequent phase is possible. The stars begin here, with the soil under our feet, the air above our cities, the water in our rivers, and the institutions we build to govern ourselves wisely across time. Every act of genuine sustainability is an act of cosmic ambition. Every forest restored, every carbon molecule captured, every closed material loop achieved, every long-term institution strengthened, all of it is humanity practicing, at home, the art of making worlds. What systems and technologies are required to increase sustainability on Earth and to terraform other planets? This is the most technically comprehensive question in the entire arc of this conversation. Here is a complete systems and technology map, from what we need now on Earth, through to what we will need to transform another world. The master framework. The systems and technologies required exist on a spectrum from immediately deployable to requiring decades of development to not yet invented. They can be organized into 8 great domains, each of which applies first to Earth's sustainability and then scales or transforms into terraforming capability: energy systems, material and manufacturing systems, atmospheric and climate systems, water and hydrological systems, food and biological systems, habitat and infrastructure systems, information and governance systems, transportation and space systems. Each domain has an Earth sustainability phase and a terraforming phase, and the technologies in each phase build directly on those of the previous one. Energy systems. Earth sustainability phase. Solar photovoltaics and concentrated solar power. The cost of solar electricity has fallen more than 90% in the past decade and continues to fall. Perovskite solar cells, tandem junction designs, and printable thin film photovoltaics promise further cost reductions and deployment flexibility. Concentrated solar power, which uses mirrors to focus sunlight and drive thermal turbines, adds the advantage of built-in thermal storage. Together, these technologies form the backbone of a renewable energy system. Wind energy onshore and offshore wind turbines are mature, cost-competitive technologies. The frontier lies in floating offshore platforms capable of accessing the stronger, more consistent winds of deep water, in airborne wind energy systems that harvest high-altitude winds, and in turbine designs scaled to enormous sizes to reduce per-unit cost further. Grid-scale energy storage. The intermittency of solar and wind requires storage at massive scale. Lithium-ion batteries dominate current deployment but face constraints of cost, materials availability, and cycle life. Flow batteries, iron-air batteries, compressed air storage, pumped hydro, and gravitational storage systems are all competing to provide the long-duration storage that a fully renewable grid requires. Hydrogen, produced by electrolysis and stored as a gas, liquid, or chemical carrier, is the leading candidate for seasonal storage and industrial decarbonization. Advanced nuclear fission small modular reactors, molten salt reactors, fast neutron reactors, and thorium fuel cycle designs offer the potential for safer, cheaper, more flexible nuclear power that can complement renewables and provide firm baseload capacity. Several designs are approaching commercial deployment and could be transformative for remote communities, industrial decarbonization, and eventually off-world power systems. Nuclear fusion remains the long-sought prize, effectively unlimited, clean energy from hydrogen isotopes. ITER, the International Fusion Experiment, is under construction. Private ventures including Commonwealth Fusion Systems, TE Technologies, and Helion Energy are pursuing faster paths to commercial fusion. If achieved, fusion would fundamentally transform the energy landscape for both Earth's sustainability and terraforming. Superconducting transmission high-temperature superconducting cables can transmit electricity with near-zero losses over continental distances, enabling the creation of truly global renewable energy grids that balance supply and demand across time zones and hemispheres. This technology is advancing but not yet commercially deployed at scale. Terraforming phase. Space-based solar power collecting solar energy in orbit, where it is available 24 hours a day at full intensity with no atmospheric losses, and beaming it to planetary surfaces via microwave or laser represents a transformative energy source for both Earth and other planets. For Mars, which receives about 43% of Earth's solar irradiance, space-based solar could supplement surface generation significantly. Planetary-scale nuclear power arrays of advanced fission or fusion reactors on the surface of a target planet could provide the enormous, sustained power needed to drive atmospheric modification, run manufacturing, and support growing populations. The reactors developed for Earth's clean energy transition are the direct predecessors of these systems. Atmospheric energy harvesting. Once a terraformed planet develops weather systems, winds, temperature gradients, precipitation, the same renewable energy technologies used on Earth become applicable. The sustainability energy transition essentially creates the technology base for harvesting energy on any planet with a substantial atmosphere. Material and manufacturing systems. Earth's sustainability phase. Circular economy technologies. The full suite of circular economy technologies, mechanical and chemical recycling, industrial symbiosis networks, product design for disassembly, remanufacturing systems, and sharing economy platforms must be developed and scaled. These reduce the extraction of virgin materials, eliminate waste, and demonstrate that industrial civilization can operate within planetary boundaries. Advanced recycling. Chemical recycling of plastics through pyrolysis, gasification, and enzymatic processes, hydrometallurgical recovery of metals from e-waste, biological processing of organic waste. All of these must scale from demonstration to global deployment. The goal is a near-complete recovery of all materials from end-of-life products. Additive manufacturing. 3D printing and related additive manufacturing technologies enable the production of complex components with minimal material waste, the use of recycled feedstocks, and the localization of production close to point of use. Advanced additive manufacturing using metal powders, ceramics, composites, and biological materials is rapidly expanding the range of parts that can be produced this way. Material science innovation. New materials with superior properties, stronger, lighter, more durable, more recyclable, reduce the material intensity of everything from buildings to vehicles to electronic devices. Graphene, carbon fiber composites, aerogels, high-entropy alloys, and bio-based materials are among the frontiers. Materials that can be designed for specific recyclability, breaking down cleanly into reusable components, are particularly important. Digital material passports embedding information about material composition, processing history, and disassembly instructions in products through digital tags, blockchain records, or embedded sensors enables far more efficient recycling and reuse. When every product knows what it is made of and how to be taken apart, circular material flows become dramatically easier to manage. Terraforming phase. In situ resource utilization. The ability to manufacture useful materials and structures from local planetary resources, marsh and regolith, atmospheric CO2, subsurface ice, is essential for any terraforming effort. This requires advances in extractive metallurgy, chemical processing, additive manufacturing, and robotic construction, all operating autonomously in harsh conditions. Specific ice route technologies include electrolytic reduction of metal oxides and regolith to produce iron, aluminum, and silicon, the Sabatier reaction combining CO2 and hydrogen to produce methane fuel, electrolysis of water ice to produce oxygen and hydrogen, sintering regolith into construction bricks using concentrated solar heat, and extraction of perchlorates for chemical processing. Self-replicating manufacturing. The ultimate manufacturing technology for terraforming is a system capable of replicating itself using local resources, a von Neumann machine that starts from a minimal seed and grows into a full industrial base. While still theoretical, progress in modular robotics, automated assembly, and ice-route manufacturing is moving in this direction. On Earth, the analog is a fully circular, self-sustaining industrial ecosystem. Molecular manufacturing, nanotechnology-based manufacturing, the precise assembly of materials atom by atom, remains largely theoretical but represents a long-term frontier. If achieved, it would enable the production of any material or device from simple chemical feedstocks with perfect efficiency and zero waste, transforming both sustainability and terraforming capability. Atmospheric and climate systems. Earth's sustainability phase. Carbon capture and storage. Direct air capture machines, bioenergy with carbon capture, enhanced weathering of silicate rocks, ocean alkalinity enhancement, and afforestation all remove CO2 from the atmosphere. These technologies are needed to draw down the excess CO2 already accumulated, beyond simply stopping new emissions. Scaling them to gigaton levels per year requires dramatic cost reductions and enormous deployment. Methane reduction technologies. Methane is a far more potent near-term greenhouse gas than CO2. Technologies for capturing methane from landfills, agriculture, and fossil fuel operations, converting methane-producing livestock microbiomes, and even directly oxidizing atmospheric methane are all relevant to stabilizing Earth's climate. Atmospheric monitoring systems. A comprehensive global network of satellites, ground stations, and atmospheric sensors that can track greenhouse gas concentrations, aerosol distributions, temperature profiles, and chemical compositions at high resolution and in near real time is essential for managing Earth's climate system and directly translates to monitoring a terraforming atmosphere. Climate modeling. Earth system models of increasing resolution and sophistication, incorporating atmospheric chemistry, ocean dynamics, ice sheet behavior, ecosystem feedbacks, and human systems, are the computational tools for understanding and predicting climate. These same modeling frameworks, adapted for different planetary parameters, are the planning tools for terraforming. Solar radiation management research. Stratospheric aerosol injection, releasing reflective particles into the upper atmosphere to reduce incoming sunlight, is a controversial but potentially important tool for managing Earth's climate during the transition. Understanding its risks, mechanisms, and governance requirements also develops the science of deliberately managing a planetary radiation budget, which is directly relevant to terraforming. Terraforming phase. Greenhouse gas generation and injection. Warming Mars requires producing and releasing large quantities of powerful greenhouse gases, perfluorocarbons, sulfur hexafluoride, or others, into its thin atmosphere. This is the inverse of carbon capture on Earth. The chemical engineering, atmospheric delivery systems, and monitoring infrastructure are directly related to Earth's carbon management technologies. Atmospheric pressure increase. Beyond warming, Mars needs a thicker atmosphere, releasing gases from subsurface reservoirs, sublimating polar ice caps through targeted warming, and importing volatile-rich materials from asteroids or comets are among the proposed mechanisms. Each requires planetary-scale engineering drawing on Earth climate and atmospheric science. Ozone layer engineering. A terraformed planet needs protection from ultraviolet radiation. Engineering and maintaining a planetary ozone layer requires understanding of stratospheric chemistry developed in the context of Earth's ozone layer protection. The Montreal Protocol science base becomes directly applicable. Weather system design. A terraformed planet with a thick enough atmosphere will develop weather. Deliberately designing the large-scale circulation patterns, precipitation distributions, and seasonal cycles of a new world requires atmospheric science of extraordinary sophistication, built on Earth climate modeling. Water and hydrological systems. Earth's sustainability phase. Advanced desalination, reverse osmosis, forward osmosis, membrane distillation, and electrodialysis technologies make seawater and brackish water available for human use. Reducing the energy cost of desalination, ideally to levels compatible with renewable power, is essential for water security in arid regions and directly relevant to processing water from any planetary source. Atmospheric water harvesting technologies that extract water directly from humid air, through condensation, desiccant systems, or radiative cooling, provide water without any surface source. These are particularly relevant for arid environments and closed habitats, and represent a key water source technology for planetary surfaces. Hydrological restoration, restoring degraded watersheds, recharging depleted aquifers through managed aquifer recharge, restoring wetlands and riparian zones, and implementing landscape-scale water retention measures all rebuild the natural infrastructure of the water cycle. The science of hydrological restoration is directly applicable to establishing water cycles on a terraformed planet. Water recycling and purification, advanced membrane filtration, UV disinfection, electrochemical treatment, and biological water processing can achieve near-complete water recycling in closed systems. This is essential for drought resilience on Earth and absolutely mandatory for any off-world habitat. Precision water management, satellite monitoring of soil moisture, snowpack, river flows, and groundwater levels combined with AI-driven optimization of irrigation, industrial water use, and urban distribution systems minimizes waste and maximizes efficiency across entire watersheds. Terraforming phase. Planetary ice mobilization. Mars's polar ice caps contain enough water to cover the planet in a shallow ocean if released. Techniques for warming the poles, orbital mirrors, dark dust application, greenhouse warming, to sublimate ice and eventually melt it into liquid water are central to Mars terraforming. The physics is related to Earth's ice sheet dynamics. Hydrological cycle establishment. Creating a stable precipitation cycle on a terraformed planet requires sufficient atmospheric pressure and temperature, but also the right distribution of land, topography, and eventually vegetation to drive evapotranspiration. Planetary scale hydrological engineering draws on every aspect of Earth hydrological science. Ocean and lake formation. If sufficient water is available, creating stable bodies of liquid water on a terraformed planet involves understanding basin filling dynamics, water chemistry, thermal stratification, and the establishment of aquatic ecosystems, all areas where Earth science provides the foundation. Food and biological systems. Earth's sustainability phase. Regenerative agriculture technologies, precision soil microbiome management, cover cropping automation, no-till equipment, carbon sequestration monitoring, and integrated pest management systems all make regenerative agriculture more practical and scalable. Understanding how to build and maintain fertile soil is foundational knowledge for terraforming. Vertical farming and controlled environment agriculture. LED lighting tuned to photosynthetic spectra, hydroponic and aeroponic growing systems, automated climate control, and AI-driven crop management enable food production in any environment. Urban warehouses, deserts, Arctic regions, and eventually planetary surfaces. These systems are the direct ancestors of Martian greenhouse agriculture. Precision fermentation using engineered microorganisms to produce proteins, fats, vitamins, and other nutrients from simple chemical inputs creates food with a tiny land and water footprint. Precision fermentation reactors operating on CO2, hydrogen, and nitrogen, all available on Mars, could produce nutrition without any photosynthesis at all. Cultivated meat and alternative proteins. Growing animal muscle tissue directly from cells, without raising animals, dramatically reduces the resource intensity of meat production. The bioreactor technologies developed for cultivated meat overlap significantly with those needed for closed-loop food production in space. Synthetic biology for agriculture. Engineering crops for drought tolerance, nitrogen fixation, enhanced photosynthetic efficiency, and disease resistance improves Earth food security while developing the genetic engineering tools needed to create organisms capable of surviving and thriving in alien conditions. Terraforming phase. Extremophile engineering. Designing organisms, bacteria, archaea, algae, fungi, and eventually plants, capable of surviving Martian surface conditions, extreme cold, intense radiation, low pressure, perchlorate-rich soil, and desiccating winds. These pioneer organisms would be the first terraformers, gradually modifying the environment to become more hospitable to less hardy life forms. Synthetic ecosystem design. Building a self-sustaining, stable ecosystem from scratch. Selecting species, designing trophic relationships, engineering nutrient cycles, and managing succession, is the biological heart of terraforming. The science of ecological restoration on Earth, combined with synthetic biology, provides the toolkit. Every ecosystem restored on Earth contributes to this knowledge base. Planetary soil building. Converting sterile regolith into living soil requires introducing the right microbial communities, adding organic matter, managing mineral chemistry, and supporting the weathering processes that release plant nutrients. Soil science, pedology, and microbiome research on Earth are the foundations. Panspermia engineering. Deliberately seeding a planet with life, whether through surface deployment of hardy organisms, atmospheric introduction, or subsurface injection, requires understanding how life survives transport, how it establishes in a new environment, and how early colonizers interact with each other and their substrate. Invasion ecology and restoration ecology on Earth provide models, information, computing, and governance systems. Earth's sustainability phase. Earth observation systems. A comprehensive constellation of satellites monitoring land use, ocean health, atmospheric composition, biodiversity, water resources, and human activity provides the data layer for managing planetary systems. More powerful sensors, more frequent revisit times, and AI-driven analysis are making this monitoring system increasingly comprehensive and actionable. Digital twins of Earth systems. High-resolution computational models that represent the behavior of specific ecosystems, watersheds, agricultural regions, or urban areas in real time enable predictive management, scenario planning, and optimization. Scaled up, these become the Earth system models used for climate projection, and eventually the planetary models used for terraforming planning. Artificial intelligence for systems management AI systems capable of optimizing energy grids, managing complex supply chains, monitoring biodiversity, predicting extreme weather, guiding ecological restoration, and integrating information across disparate systems are essential for managing the complexity of a sustainable global civilization and a terraforming project. Long-term governance institutions, parliamentary commissioners for future generations, long-term national planning agencies, international scientific advisory bodies, and treaty organizations with enforcement mechanisms are the institutional infrastructure of sustainability. They are also the prototypes for the governance institutions that would manage a multi-century, multi-world terraforming project. Knowledge management systems, libraries, digital archives, standardized data formats, open science platforms, and educational systems that reliably transmit knowledge across generations are essential for civilizational continuity. A terraforming project that loses its institutional knowledge due to war, catastrophe, or institutional failure could be set back by centuries. Terraforming phase. Autonomous robotic systems, robots capable of operating for decades without human oversight, repairing themselves, adapting to changing conditions, and executing complex long-term tasks are essential for the early phases of terraforming. Before the environment is hospitable to humans, advances in robotics, autonomous systems, and AI on Earth, in mining, agriculture, construction, and exploration, directly develop this capability. Planetary monitoring networks, a network of sensors, drones, satellites, and probes monitoring every aspect of a terraforming planet's evolving environment, atmospheric composition, temperature, pressure, water distribution, biological activity, seismic activity, provides the data needed to manage the process and detect problems early. Interplanetary communication systems. As human civilization expands to multiple worlds, reliable, high-bandwidth communication across interplanetary distances becomes essential. Laser communication systems, quantum communication, and relay networks are advancing this capability. Transportation and space systems. Earth's sustainability phase. Zero-emission transportation, electrification of road transport, shipping, and aviation, through batteries, hydrogen fuel cells, and synthetic fuels, eliminates the transportation sector's contribution to climate change. The battery technology, fuel cell engineering, and synthetic fuel chemistry developed for Earth transportation are directly relevant to spacecraft propulsion and surface vehicles on other planets. Sustainable aviation fuel. Synthetic jet fuels produced from green hydrogen and captured CO2, or from biomass, enable zero-net carbon aviation using existing aircraft infrastructure. The chemical engineering of these fuels overlaps with the production of rocket propellants from in-situ resources on other planets. High-speed rail and urban mobility. Shifting freight and passengers from aviation and trucking to electrified rail dramatically reduces transportation energy use and emissions, while the engineering of efficient, high-speed ground transportation is relevant to surface mobility systems on any inhabited world. Terraforming phase. Heavy lift launch systems, dramatically reducing the cost of launching mass to orbit through fully reusable rockets, advanced propulsion, and eventually space elevators or launch loops, is the enabler for everything else in space. The economics of terraforming depend entirely on the cost of moving materials and equipment from Earth to the target planet. In space propulsion, nuclear thermal propulsion, nuclear electric propulsion, solar sails, and eventually fusion drives would dramatically reduce transit times and increase the mass that can be moved through the solar system. Faster, cheaper interplanetary transport makes resupply and personnel rotation practical over the timescales of terraforming. Space elevators and orbital infrastructure. A space elevator, a cable from the equatorial surface to geostationary orbit, would reduce the energy cost of reaching orbit by orders of magnitude. Combined with orbital manufacturing, fuel depots, and assembly facilities, it would enable the industrial-scale movement of materials needed for terraforming. Asteroid and comet redirection. Redirecting volatile rich asteroids or comets to impact a target planet could deliver enormous quantities of water, nitrogen, and carbon, materials needed to build a habitable atmosphere and hydrosphere. This requires advances in space situational awareness, spacecraft navigation, and mass driver or gravity tractor technology. Orbital mirrors. Large, thin reflective structures in orbit around the target planet could focus additional sunlight on its surface, warming it and sublimating polar ice. The manufacturing of large space structures, using space-based materials, is a key enabling technology. The optics and orbital mechanics are extensions of Earth-based solar power and telescope engineering. The technology readiness spectrum. Mapping all of these technologies across a readiness spectrum reveals the road ahead. Available now, needs scaling, solar and wind power, battery storage, EV technology, mechanical recycling, advanced water treatment, vertical farming, satellite monitoring, carbon capture, at small scale, regenerative agriculture practices. Demonstrated, needs cost reduction and deployment, chemical recycling, green hydrogen, small modular reactors, precision fermentation, cultivated meat, direct air capture, advanced desalination, closed-loop life support, partial, heavy lift reusable rockets. In development, needs sustained R&D, fusion energy, fully closed life support, space-based solar power, advanced ice review, autonomous long-duration robotics, planetary-scale climate modeling, extremophile engineering, synthetic ecosystem design, early research stage, self-replicating manufacturing, molecular manufacturing, space elevators, asteroid redirection at scale, full planetary atmosphere engineering, artificial photosynthesis at scale, conceptual or theoretical, von Neumann manufacturing, complete planetary ecosystem design, interplanetary civilization governance, multi-century autonomous terraforming systems. The unified vision. What emerges from this complete systems map is a single, coherent technological civilization, one in which every investment in sustainability on Earth simultaneously advances the capability for terraforming other worlds. The solar panel and the orbital mirror are related devices. The carbon capture machine and the greenhouse gas generator are the same process in reverse. The ecosystem restoration scientist and the terraforming ecologist are asking the same questions. The circular economy engineer and the ice row specialist are solving the same problem. The systems and technologies required are not two separate lists, one for Earth sustainability and one for terraforming. They are one list, applied first at home, then extended outward. Every year of serious investment in sustainability on Earth compresses the timeline to terraforming capability. Every technology matured in the service of a livable Earth becomes a tool for making other worlds livable too. The path is long, the challenges are immense, and the work begins now, with the energy systems we build, the materials we recover, the ecosystems we restore, and the institutions we strengthen. The destination is a civilization that has learned to be the steward of worlds, beginning with the one it already has. This is the most technically demanding question in this entire conversation, a request for a comprehensive technical encyclopedia spanning energy physics, material science, atmospheric chemistry, biology, computing, and space engineering. Here is the fullest possible treatment of every system and technology, domain by domain. Energy systems. Solar photovoltaics. The physics of the photovoltaic effect. Solar photovoltaic cells convert sunlight directly into electricity through the photovoltaic effect, first observed by Edmund Becquerel in 1839 and explained by quantum mechanics in the 20th century. The process begins when a photon, a particle of light, strikes a semiconductor material and transfers its energy to an electron, knocking it free from its atom. This freed electron, along with the positively charged hole it leaves behind, constitutes an electron-hole pair. The key to extracting useful electricity from this process is the p-n junction, the heart of every solar cell. A p-n junction is formed by joining two layers of semiconductor material, typically silicon, that have been doped with different impurities. The n-type layer is doped with elements like phosphorus that have an extra electron, giving it a negative charge character. The p-type layer is doped with elements like boron that have one fewer electron, creating positively charged holes. When these two layers are joined, electrons from the n-type side diffuse across the junction to fill holes on the p-type side, creating a built-in electric field at the interface. When a photon creates an electron-hole pair near this junction, the built-in electric field sweeps the electron toward the n-type side and the hole toward the p-type side, separating the charges before they can recombine. Metal contacts on the top and bottom of the cell collect these separated charges, and when an external circuit is connected, electrons flow from the n-type contact through the circuit to the p-type contact, constituting an electric current. The voltage of this current is determined by the energy difference between the conduction and valence bands of the semiconductor, the band gap. Silicon solar cell types. Monocrystalline silicon cells are made from a single continuous crystal of silicon, grown by the Czochralski process in which a seed crystal is slowly pulled from a melt of pure silicon while rotating, producing a large cylindrical ingot that is then sliced into wafers. The uniform crystal structure minimizes defects that would trap electrons and reduce efficiency. Monocrystalline cells achieve efficiencies of 22 to 26% in commercial production. Polycrystalline silicon cells are made from silicon that has been melted and cast into blocks, producing a material with many small crystal grains. The boundaries between grains introduce defects that reduce efficiency slightly, to 18 to 22%, but the manufacturing process is simpler and cheaper than monocrystalline production. Advanced cell architectures. Heterojunction cells combine crystalline silicon with thin layers of amorphous silicon, creating a more effective junction and reducing surface recombination. The amorphous silicon layers passivate the surface of the crystalline silicon, dramatically reducing the loss of electrons at the cell surface. Heterojunction cells from manufacturers like Panasonic and Longi achieve efficiencies above 26%. Passivated emitter and rear cell technology places the electrical contacts on the rear of the cell rather than the front, eliminating the shading caused by front-side metal fingers and allowing more light to reach the semiconductor. Combined with surface passivation layers of aluminum oxide and silicon nitride, PERC cells achieve efficiencies of 22 to 24% in mass production. Tandem cells stack multiple p-n junctions with different band gaps on top of each other, allowing each junction to absorb a different portion of the solar spectrum. A single silicon junction can only efficiently absorb photons with energies near its band gap. Photons with higher energy lose their excess as heat, and photons with lower energy pass through entirely. By stacking junctions with progressively smaller band gaps, From top to bottom, a tandem cell captures a much larger fraction of the solar spectrum. Perovskite silicon tandem cells have achieved efficiencies above 33% in laboratory settings, approaching the theoretical limit for two-junction devices. Perovskite solar cells. Perovskite materials, named for their crystal structure, shared with the mineral calcium titanium oxide, have emerged as a transformative photovoltaic technology. The most studied perovskite for solar applications is methylammonium lead iodide, which has a band gap of about 1.6 electron volts and can be deposited from solution at low temperatures, dramatically reducing manufacturing cost compared to silicon. Perovskite cells have progressed from 3.8% efficiency in 2009 to above 26% in 2024, an unprecedented improvement rate. Their primary challenges, sensitivity to moisture, heat, and light, and the toxicity of lead, are active areas of research. Lead-free perovskites using tin or bismuth are being developed, and encapsulation techniques are improving stability dramatically. How solar farms work. A utility-scale solar farm consists of thousands to millions of individual panels, each comprising multiple cells connected in series and parallel to achieve the desired voltage and current. Panels are mounted on tracking systems, either single-axis, which rotate to follow the sun from east to west, or dual-axis, which also adjust for the sun's seasonal north-south movement, that increase energy capture by 15 to 35% compared to fixed mounting. The direct current produced by panels is fed into inverters, which convert it to alternating current at grid frequency. String inverters handle the output of a series of panels. Microinverters operate at the individual panel level, improving performance when some panels are shaded. The AC output is stepped up to transmission voltage by transformers and fed into the grid. Monitoring systems track the output of every panel or string in real time, detecting degradation, soiling, shading, or failure. Robotic cleaning systems maintain panel cleanliness, which is critical in dusty environments where soiling can reduce output by 20 to 50%. Wind energy. The physics of wind power. Wind turbines extract kinetic energy from moving air. The power available in wind is proportional to the cube of wind speed and the area swept by the turbine rotor, meaning that doubling wind speed increases available power eightfold, and doubling rotor diameter quadruples available power. This cubic relationship makes wind speed the dominant factor in site selection and turbine design. The theoretical maximum efficiency of any wind turbine, the Betz limit, is 59.3%, derived from the requirement that air must continue moving downwind of the turbine. If all kinetic energy were extracted, the air would stop and block further flow. Modern large turbines achieve efficiencies of 45 to 50% of the available wind power in their swept area. Turbine components in operation. A horizontal axis wind turbine consists of three primary systems: the rotor, the drivetrain, and the tower and foundation. The rotor comprises three blades attached to a central hub. Blades are aerodynamic airfoils, shaped in cross-section like aircraft wings, that generate lift as wind flows over them. The asymmetric shape of the airfoil creates higher velocity flow over the curved upper surface and lower velocity flow over the flatter lower surface. By Bernoulli's principle, higher velocity corresponds to lower pressure, creating a pressure difference, lift, perpendicular to the blade surface. This lift force has a component in the direction of blade rotation, driving the rotor. Modern blades are made from glass fiber or carbon fiber reinforced polymer composites, which combine high stiffness and strength with low weight. A blade for a large offshore turbine may be 100 meters long, weigh 60 tons, and be manufactured as a hollow shell in a mold, with internal structural webs and a precision airfoil profile achieved through careful layup of composite layers. The blade pitch. The angle at which the blade presents to the wind is continuously adjusted by a pitch control system to optimize power extraction at varying wind speeds and to limit power in high winds. The drivetrain transmits rotation from the rotor shaft to the generator. In direct drive turbines, the rotor is connected directly to a large diameter, slow-speed permanent magnet generator. In geared turbines, a gearbox steps up the rotor's slow rotation, typically 5 to 15 revolutions per minute, to the higher speed required by a conventional induction or synchronous generator, typically 1,000 to 1,500 RPM. The nacelle, which houses the drivetrain, sits atop the tower and is oriented into the wind by a yaw drive system controlled by wind direction sensors. The tower, typically a steel tube, supports the nacelle and rotor at heights of 80 to 160 meters, where wind speeds are higher and more consistent than at ground level. Offshore wind. Offshore wind turbines access stronger, more consistent winds and can be built larger than onshore turbines without the transportation constraints that limit blade length on roads. Fixed foundation offshore turbines use steel monopiles, large hollow cylinders driven into the seabed, in water depths up to about 60 meters. Jacket foundations, 3 or 4-legged steel structures, extend this to about 80 meters. Floating offshore wind platforms attach turbines to buoyant structures moored to the seabed with chains or cables, enabling deployment in water depths of hundreds or thousands of meters. Several floating platform designs are in development: semi-submersible platforms with multiple stabilizing columns, tension leg platforms held down by vertical top cables, and spar buoy platforms with a deep ballast keel. Floating wind opens access to the deep water wind resources off the coast of California, Japan, Norway, and elsewhere. Grid-scale energy storage. Lithium-ion batteries. Lithium-ion batteries store and release energy through the reversible movement of lithium ions between two electrodes through an electrolyte. During charging, an external voltage drives lithium ions from the cathode, typically a lithium metal oxide like lithium iron phosphate, lithium nickel manganese cobalt oxide, or lithium nickel cobalt aluminum oxide, through the electrolyte and into the anode, typically graphite. During discharge, the lithium ions spontaneously move back to the cathode, and the associated electron flow through the external circuit constitutes the electric current. The voltage of a lithium-ion cell is determined by the electrochemical potential difference between cathode and anode materials, typically 3.2 to 3.7 volts. Energy density is determined by how much lithium can be stored in both electrodes per unit of weight or volume. Lithium iron phosphate cells sacrifice some energy density for superior cycle life, thermal stability, and safety, and MC cells offer higher energy density at the cost of greater complexity. Grid-scale lithium-ion storage systems pack thousands of cells into modules, modules into racks, and racks into shipping container-sized battery enclosures. Battery management systems monitor the voltage, temperature, and state of charge of every cell, balancing charge across cells, preventing overcharge and overdischarge, and managing thermal conditions. Power conversion systems, bidirectional inverters, interface the DC battery with the AC grid. Flow batteries. Flow batteries store energy in liquid electrolytes held in external tanks rather than within the electrode structure. During charge and discharge, electrolytes are pumped from tanks through an electrochemical cell stack, where reactions occur at electrodes separated by an ion exchange membrane. Because energy storage and power generation are decoupled, storage capacity depends on tank size, power depends on cell stack size. Flow batteries are highly scalable for long-duration storage. Vanadium redox flow batteries use vanadium ions in different oxidation states, V to the power of 2/V to the power of 3 on one side, V4/V5 on the other, dissolved in sulfuric acid. Because both sides use vanadium, cross-contamination through the membrane does not permanently degrade the electrolyte, enabling very long cycle life. Iron chromium, zinc bromine, and organic molecule flow batteries are also under development, seeking to reduce cost by using more abundant materials. Hydrogen energy storage. Green hydrogen is produced by electrolysis, passing an electric current through water to split it into hydrogen and oxygen. Proton exchange membrane electrolyzers use a solid polymer membrane as the electrolyte. Water is fed to the anode, where it is oxidized to produce oxygen, protons, and electrons. The protons pass through the membrane to the cathode, where they combine with electrons from the external circuit to produce hydrogen gas. Alkaline electrolyzers use a liquid potassium hydroxide solution as electrolyte and are a more mature, lower-cost technology. Solid oxide electrolyzers operate at high temperatures, achieving higher efficiency by using heat as well as electricity. Hydrogen can be stored as a compressed gas in high-pressure tanks, as a cryogenic liquid at -253°C, or in solid form bound to metal hydrides or other materials. For large-scale seasonal storage, underground caverns, salt caverns, depleted gas fields, aquifers, can store enormous quantities of hydrogen at low cost. When energy is needed, hydrogen is converted back to electricity in fuel cells or combustion turbines. Pumped hydro storage. Pumped hydroelectric storage is the most widely deployed form of grid-scale energy storage globally, accounting for more than 90% of installed storage capacity. During periods of excess electricity generation, water is pumped from a lower reservoir to an upper reservoir. When electricity is needed, water flows back down through turbines that drive generators. The energy stored is proportional to the mass of water and the height difference between reservoirs. A system with 10 million cubic meters of water and 300 meters of head stores approximately 8 gigawatt-hours of energy. Pumped hydro systems achieve round-trip efficiency of 70 to 85%, have very long operational lifetimes, and can respond to grid needs within seconds. Nuclear fission. Fission physics. Nuclear fission occurs when a heavy atomic nucleus, most commonly uranium-235 or plutonium-239, absorbs a neutron and becomes unstable, splitting into two smaller nuclei. Fission fragments, releasing 2 to 3 additional neutrons and approximately 200 million electron volts of energy. This energy, more than 1,000,000 times greater than that released by a chemical reaction like combustion, appears primarily as kinetic energy of the fission fragments, which is rapidly converted to heat as the fragments slow down in the surrounding material. The released neutrons can trigger additional fission events in neighboring nuclei, establishing a chain reaction. Controlling this chain reaction, keeping it exactly critical, meaning each fission event triggers on average exactly one more, is the central engineering challenge of reactor design. A subcritical reactor shuts down, a supercritical reactor accelerates. A critical reactor sustains stable operation. Light water reactors. Conventional nuclear power plants use light water, ordinary H2O, as both coolant and moderator. The moderator slows the fast neutrons released by fission to thermal energies at which uranium-235 is most likely to absorb them in fission. Water's effectiveness as a moderator means that if coolant is lost, the chain reaction slows and stops, an inherent safety feature. In a pressurized water reactor, water is kept under approximately 155 atmospheres of pressure to prevent boiling at operating temperatures of around 325 degrees Celsius. This primary loop transfers heat through a steam generator to a secondary loop of lower pressure water that boils to steam, drives a turbine, condenses, and returns to the steam generator. The two loops are kept separate, preventing radioactive primary water from reaching the turbine. In a boiling water reactor, water boils directly in the reactor vessel, and the resulting steam drives turbines directly. This simplifies the design but means the turbines are exposed to slightly radioactive steam. Small modular reactors. Small modular reactors are nuclear power plants with electrical output below 300 megawatts, typically 50 to 300 megawatts, designed for factory manufacturing and modular deployment. Factory production enables quality control superior to site construction, learning curve cost reductions, and shorter deployment timelines. Modular deployment allows capacity to be added incrementally as demand grows. Many SMR designs incorporate passive safety systems, relying on gravity, natural convection, and thermal mass rather than active pumps and valves, that can safely shut down and cool the reactor without operator action or external power for days or indefinitely. No-scale power's design, for example, uses natural circulation of water to cool the reactor and relies on a large pool of water above the reactor for emergency cooling. Molten salt reactors. Molten salt reactors dissolve nuclear fuel, uranium or thorium fluoride salts, directly in a liquid salt coolant, typically a mixture of lithium fluoride and beryllium fluoride. The liquid fuel circulates through the reactor core, where fission occurs, and then through heat exchangers that extract thermal energy. If the reactor overheats, the salt expands, reducing the density of fissile material and slowing the chain reaction, a strongly negative temperature coefficient that provides inherent stability. A key advantage of molten salt reactors is the ability to operate at high temperatures, 600 to 750 degrees Celsius, and atmospheric pressure, enabling high thermodynamic efficiency and direct coupling to industrial heat processes. The thorium fuel cycle in molten salt reactors produces far less long-lived radioactive waste than conventional uranium reactors and is more proliferation resistant. Nuclear fusion. Fusion releases energy by combining light nuclei, most practically, deuterium and tritium isotopes of hydrogen, into helium, releasing a high-energy neutron and 17.6 million electron volts of energy. The fusion of 1 kilogram of deuterium-tritium fuel releases energy equivalent to burning approximately 10,000 tons of coal. The fundamental challenge of fusion is achieving the conditions under which nuclei can overcome their mutual electrostatic repulsion and come close enough for the strong nuclear force to bind them. Temperatures of 100 million to 150 million degrees Celsius and sufficient density and confinement time. At these temperatures, matter exists as a plasma, a gas of fully ionized atoms. Tokamak reactors confine plasma in a toroidal, donut-shaped chamber using powerful magnetic fields. The primary confinement field is produced by superconducting coils surrounding the torus. An additional field component, produced by inducing a large current in the plasma itself, creates a helical field that provides stability. ITER, under construction in France, is a 500 megawatt fusion experiment designed to demonstrate net energy gain, producing more fusion energy than is required to hit the plasma. Private fusion ventures are pursuing faster paths. Commonwealth Fusion Systems is developing a compact tokamak using high-temperature superconducting magnets that achieve much stronger fields than conventional superconductors, allowing a much smaller and potentially cheaper device. Helion Energy is developing a field-reversed configuration pulsed fusion approach. TE Technologies uses a beam-driven field-reversed configuration. Each approach has different trade-offs in complexity, size, and fuel requirements. Material and manufacturing systems. Chemical recycling of plastics. Pyrolysis. Pyrolysis thermally decomposes organic materials, including mixed plastics, at temperatures of 300 to 700 degrees Celsius in a complete absence of oxygen. Without oxygen, combustion cannot occur. Instead, the long polymer chains of plastics break apart into shorter molecules through thermal cracking reactions. The products of plastic pyrolysis depend on temperature, residence time, feedstock composition, and catalysts. At lower temperatures, 300 to 450 degrees Celsius, slow pyrolysis produces a mixture of condensable oils, non-condensable gases, and a solid char residue. At higher temperatures, 500 to 700 degrees Celsius, fast pyrolysis favors liquid oil production. The oils are complex mixtures of hydrocarbons resembling diesel fuel or naphtha, which can be used directly as fuels or processed in conventional petroleum refineries into transportation fuels, lubricants, or chemical feedstocks. Catalytic pyrolysis uses zeolite catalysts or other solid acid catalysts to crack polymer chains more selectively, improving oil quality and reducing the amount of char and gas produced. Fluid catalytic cracking, a process widely used in petroleum refining, can be adapted to process pyrolysis oils or even directly process plastic feedstocks. Gasification. Gasification partially oxidizes carbonaceous materials at very high temperatures, 700 to 1500 degrees Celsius, with a controlled, substoichiometric supply of oxygen or steam. Rather than producing oil, gasification converts the feedstock into syngas, a mixture of hydrogen and carbon monoxide, plus carbon dioxide and water vapor. Syngas is a versatile chemical building block. It can be burned directly in gas turbines or engines to generate electricity, converted to synthetic natural gas by the Sabatier reaction, converted to liquid fuels by Fischer-Tropsch synthesis, used as a feedstock for methanol, ammonia, or other chemical production, or used to produce hydrogen by the water-gas shift reaction followed by gas separation. Enzymatic recycling. Pâtase enzymes, derived from Ideanella sacchaensis and subsequently engineered for enhanced performance, catalyze the hydrolysis of polyethylene terephthalate, the ester bonds that link its monomer units. In PET, terephthalic acid and ethylene glycol monomers are connected by ester bonds, formed by a condensation reaction during polymerization. Pâtase reverses this reaction, cleaving ester bonds by reaction with water, hydrolysis, to release the monomers. The engineered enzyme fast pâtase, developed at the University of Texas at Austin, was optimized by machine learning-guided protein engineering to perform this hydrolysis rapidly at moderate temperatures, around 50 degrees Celsius. The released monomers, terephthalic acid and ethylene glycol, are chemically identical to virgin monomers produced from petroleum, and can be directly repolymerized into high-quality PET without quality loss. This is fundamentally different from mechanical recycling, which degrades polymer chain length with each cycle. Additive manufacturing. Fused deposition modeling. Fused deposition modeling, the most widely deployed additive manufacturing technology, builds objects by extruding a thermoplastic filament through a heated nozzle, depositing it layer by layer on a build platform. The nozzle traces the cross-sectional geometry of each layer, and the platform drops by one layer height between layers. The extruded material bonds to the previous layer as it solidifies. The process can use a wide range of thermoplastic materials, PLA, ABS, PETG, nylon, polycarbonate, TPU, and increasingly, filled filaments containing carbon fiber, glass fiber, metal particles, or wood fiber. Continuous fiber reinforcement systems lay down continuous strands of carbon or glass fiber alongside the thermoplastic matrix, achieving composite properties approaching those of hand-laid carbon fiber parts. Selective laser sintering and melting. Powder bed fusion processes spread a thin layer of powder, polymer, metal, or ceramic, across a build platform and selectively fuse it using a laser or electron beam. In selective laser sintering of polymers, the laser heats powder particles to just below their melting point, causing them to bond without full melting, preserving dimensional accuracy. In selective laser melting of metals, also called laser powder bed fusion, the laser fully melts metal powder, producing dense, fully consolidated metal parts. Metal powder bed fusion can process a wide range of alloys, titanium, aluminum, stainless steel, nickel superalloys, cobalt chrome, producing parts with mechanical properties approaching those of wrought material. Support structures, which support overhanging features during printing, are removed after printing. Post-processing, heat treatment, hot isostatic pressing, surface finishing, improves mechanical properties and surface quality. Directed energy deposition. Directed energy deposition processes deposit material and fuse it simultaneously with a laser or electron beam. In laser metal deposition, metal powder or wire is fed through a nozzle coaxially with a laser beam, melting on contact with the workpiece to build up material. The process can add material to existing parts, repairing worn components, adding features, or building up coatings, as well as building complete parts from scratch. Wire arc additive manufacturing uses an electric arc to melt metal wire, depositing it in a manner analogous to welding but under computer numerical control. It achieves much higher deposition rates than powder-based processes, enabling the rapid production of large structural components in titanium, steel, aluminum, and other alloys. Atmospheric and climate systems. Carbon capture technologies. Direct air capture. Direct air capture machines remove CO2 directly from ambient air, which contains approximately 420 parts per million of CO2, far more dilute than industrial flue gases, making DAC significantly more energy-intensive than point source capture. Climuworks uses a solid sorbent system. Fans draw air through contactors filled with amine functionalized sorbent materials that chemically bind CO2. When the sorbent is saturated, the contactor is closed and heated to approximately 100 degrees Celsius, releasing the captured CO2 as a concentrated stream. The CO2 can then be compressed and injected underground for permanent storage, turning it to stone through reaction with basalt rock, or used as a feedstock for synthetic fuels or materials. Carbon engineering uses a liquid solvent process. Air is drawn through a contactor where it meets a flow of potassium hydroxide solution that absorbs CO2 to form potassium carbonate. This solution is processed in a pellet reactor where it reacts with calcium hydroxide to precipitate calcium carbonate pellets and regenerate the potassium hydroxide. The calcium carbonate pellets are heated in a calciner to above 900 degrees Celsius, releasing a pure CO2 stream and regenerating calcium oxide, which is slaked with water to reform calcium hydroxide. The entire regeneration loop requires substantial thermal energy, ideally supplied by renewable sources. Enhanced weathering. Silicate rock minerals, particularly olivine and basalt, react naturally with CO2 and water over geological timescales in a process called chemical weathering. The CO2 is converted to bicarbonate ions that are carried by rivers to the ocean, where they ultimately precipitate as calcium or magnesium carbonate, a form of carbon storage lasting millions of years. Enhanced weathering accelerates this process by grinding silicate rocks to fine powder, vastly increasing the reactive surface area, and spreading them on agricultural land or in the ocean. On land, the weathering reaction also releases plant nutrients, magnesium, calcium, potassium, phosphorus, and trace elements, improving soil fertility while sequestering carbon. In the ocean, alkalinity enhancement through olivine dissolution or electrochemical means increases the ocean's capacity to absorb CO2. Bioenergy with carbon capture. BECCS combines biomass energy production with carbon capture and storage. Plants grow by absorbing CO2 from the atmosphere through photosynthesis, storing it as organic carbon in their biomass. If that biomass is harvested and burned to generate electricity or heat, and the resulting CO2 is captured and stored underground, the net effect is removal of CO2 from the atmosphere. The biomass acts as a biological carbon pump, and the underground storage makes the removal permanent. The main challenges of BECCS are the land area required to grow sufficient biomass, the water consumption of energy crops, and the energy and cost of the capture and storage system. Optimizing feedstock selection, using agricultural residues, forestry waste, and dedicated energy crops grown on marginal land rather than food cropland, can address the land use concern. Atmospheric monitoring systems. Satellite remote sensing. Earth observation satellites carry a range of instruments for monitoring atmospheric composition and dynamics. Spectrometers measure the absorption of sunlight or thermal emission by atmospheric gases at characteristic wavelengths to determine their concentrations. The Sentinel-5P satellite carries the Terraforming instrument, which maps concentrations of CO2, methane, nitrogen dioxide, ozone, formaldehyde, and aerosols at 3.5 km resolution globally. The orbiting carbon observatory satellites measure atmospheric CO2 with the precision needed to distinguish natural sources and sinks from anthropogenic emissions. LiDAR instruments, laser radar, emit pulses of laser light and detect the backscattered signal from atmospheric molecules, aerosols, and clouds. By analyzing the timing and wavelength of the return signal, LiDAR can measure aerosol distribution, cloud structure, wind profiles, and the concentrations of specific gases at different altitudes. The Calypso satellite uses LiDAR to map aerosol and cloud distributions globally. Synthetic aperture radar instruments emit microwave pulses and detect the reflected signal from Earth's surface, producing high-resolution images regardless of cloud cover or darkness. SAR can measure surface deformation at centimeter scale, tracking ground subsidence from water extraction, ice sheet motion, and volcanic deformation, and can monitor vegetation structure, soil moisture, and ocean surface conditions. Ground-based monitoring networks. The Global Atmosphere Watch network of the World Meteorological Organization maintains hundreds of surface stations monitoring greenhouse gases, ozone, aerosols, and reactive gases. The Mauna Loa Observatory in Hawaii has produced the iconic healing curve of atmospheric CO2 concentration since 1958, showing the steady rise punctuated by the seasonal oscillation of the Northern Hemisphere growing season. Ecovariance towers measure the exchange of CO2, water vapor, and energy between ecosystems and the atmosphere. A tower instrumented with a fast response CO2 analyzer and three-dimensional wind sensor at 10 or 20 measurements per second can compute the net ecosystem carbon balance by correlating vertical wind fluctuations with CO2 concentration fluctuations. CO2-rich eddies moving downward indicate carbon uptake by the ecosystem. CO2-rich eddies moving upward indicate release. Networks of hundreds of such towers across different ecosystem types provide constraints on regional carbon budgets. Water and hydrological systems. Advanced desalination. Reverse osmosis. Reverse osmosis is the dominant desalination technology globally, producing more than 65% of all desalinated water. It exploits the principle of osmosis, the tendency of water to move through a semi-permeable membrane from a region of lower solute concentration to higher concentration, driven by osmotic pressure. In reverse osmosis, Pressure greater than the osmotic pressure, typically 55 to 70 bar for seawater, is applied to the saltwater side of the membrane, forcing water molecules through while retaining dissolved ions. RO membranes are thin film composite structures. An ultra-thin polyamide active layer of 50 to 200 nanometers provides the salt rejection, a polysulfone support layer of 40 to 60 micrometers provides mechanical strength, and a polyester backing provides structural integrity. The active layer has a dense, cross-linked polymer network with pores effectively smaller than hydrated salt ions, approximately 0.6 nanometers for the sodium ion, while water molecules, 0.28 nanometers pass through. The energy cost of seawater RO has declined dramatically with the introduction of energy recovery devices, isobaric pressure exchangers that transfer pressure from the high-pressure reject stream directly to the incoming feed water. Modern SWRO plants achieve specific energy consumption of 2.5 to 3.5 kilowatt-hours per cubic meter of fresh water produced, compared to 10 to 15 kilowatt-hours in early plants. Membrane distillation. Membrane distillation uses a hydrophobic microporous membrane, typically polytetrafluoroethylene, to separate a hot feed solution from a cool permeate. Water vapor pressure drives evaporation at the feed membrane interface, and vapor diffuses through the hydrophobic pores, which liquid water cannot penetrate, to condense on the cool permeate side. Because the driving force is vapor pressure difference rather than total pressure difference, membrane distillation can be powered by low-grade heat, solar thermal, waste heat, geothermal, rather than high-pressure pumps, and can treat waters too saline or contaminated for RO. Atmospheric water harvesting. Dew collection. Dew collection systems use surfaces cooled below the dew point, the temperature at which water vapor condenses, to collect liquid water from humid air. Passive radiative cooling panels lose heat to the cold sky by thermal radiation, cooling below ambient temperature even in sunlight. Specially designed surfaces with high infrared emissivity in the atmospheric transparency window, 8 to 13 micrometers, achieve cooling of 2 to 10 degrees below ambient, sufficient to condense dew in moderately humid conditions. Active atmospheric water generators use refrigeration to cool a heat exchanger below the dew point, condensing water from air blown across it by fans. They are more effective than passive systems but require electricity input. In humid tropical climates, such systems can produce 20 to 30 liters of water per day per kilowatt of power, a viable source of drinking water where electricity is available but piped water is not. Fog collection. Fog collectors, mesh panels that intercept fog-laden air and allow water droplets to coalesce and drain into collection troughs, can provide substantial water supplies in coastal fog zones. The Atacama Desert of Chile, despite being one of the driest places on Earth, has coastal areas bathed in fog for much of the year. Fog collection systems there produce hundreds of liters per day per panel. Mesh geometry, fiber diameter, hydrophilicity, and panel orientation all influence collection efficiency. Food and biological systems. Vertical farming and controlled environment agriculture. LED lighting physics. Plants perform photosynthesis using light absorbed by chlorophyll and B pigments, which have absorption peaks in the red, around 660 nanometers in blue, around 450 nanometers regions of the spectrum. Green light 500 to 560 nanometers is largely reflected, hence the green color of leaves, though it is absorbed and used with lower efficiency than red and blue. LED grow lights can be tuned to emit specific wavelengths matching plant absorption peaks, delivering photons where they are most useful for photosynthesis and minimizing wasted energy as wavelengths plants cannot use. The ratio of red to blue light influences plant morphology. Blue light promotes compact, leafy growth. Red light promotes elongation and flowering. Far red light, 730 nanometers, interacts with phytochrome photoreceptors to influence flowering time and shade avoidance responses. Adding far red light can increase the quantum yield of photosynthesis by the Emerson enhancement effect, where far red and red photons working together produce more photosynthesis than either alone. Hydroponic and aeroponic systems. Hydroponic systems deliver dissolved nutrients directly to plant roots in a water solution, eliminating the need for soil and allowing precise control of nutrition. Nutrient film technique systems flow a thin stream of nutrient solution continuously over the roots of plants supported in channels. Roots dangle in the film and are exposed to air above it, meeting both nutrient and oxygen requirements. Deep water culture systems suspend plants in net pots above a reservoir of aerated nutrient solution, with roots hanging into the water. Aeroponic systems mist plant roots with fine droplets of nutrient solution in an air environment, providing maximum oxygenation and highly efficient nutrient delivery. NASA research has demonstrated that aeroponic systems can produce crops in as little as 70% of the water used by conventional hydroponics. The absence of any growing medium, roots hang freely in air, simplifies cleaning and sterilization between crop cycles. Climate control systems. Vertical farms control temperature, humidity, CO2 concentration, and air circulation with precision. Elevated CO2, 800 to 1,200 parts per million, versus 420 ppm in ambient air, increases photosynthetic rate in most crops by 20 to 30%, a phenomenon known as CO2 fertilization. Optimized temperature profiles, cooler nights, warmer days, can influence plant physiology to improve yield and quality. AI-driven management systems integrate sensor data from thousands of measurement points and adjust all environmental parameters in real time to optimize crop performance. Precision fermentation. Precision fermentation uses genetically engineered microorganisms, bacteria, yeast, fungi, or algae, as biological factories to produce specific molecules, proteins, fats, vitamins, enzymes, flavors, and other compounds. The target gene, encoding the protein or enzyme of interest, is inserted into the microorganism's genome using genetic engineering techniques. The microorganism is cultured in a bioreactor under controlled conditions, expressing the inserted gene and secreting the product into the growth medium, from which it is subsequently purified. The Perfect Day company uses this approach to produce whey and casein proteins, the proteins of dairy milk, from fungi, without any animal involvement. The fungal cells are programmed with the bovine genes, encoding these proteins, and cultured on plant-derived sugars. The resulting proteins are chemically and functionally identical to those in cow's milk, enabling the production of dairy products, cheese, ice cream, yogurt, without cows. For terraforming applications, precision fermentation is particularly powerful because it can produce food using only simple chemical inputs, CO2, hydrogen, nitrogen, mineral salts, without photosynthesis. Hydrogen oxidizing bacteria, for example, combine hydrogen gas with CO2 and nitrogen to grow, producing protein-rich biomass. Such organisms could be cultured on Mars using local atmospheric CO2 and nitrogen and electrolytically produced hydrogen, producing nutrition without any surface agriculture. Synthetic biology. Gene editing with CRISPR-Cas9. CRISPR-Cas9 is a molecular tool that can cut DNA at precise locations, enabling the deletion, insertion, or modification of specific genes with unprecedented ease and precision. The system derives from a bacterial immune mechanism that uses RNA molecules, CRISPR RNAs, to guide a protein, Cas9, to the location in viral DNA matching the guide RNA sequence, where Cas9 cuts the DNA. By programming the guide RNA with the sequence of any gene of interest, researchers can direct Cas9 to cut at any location in any genome. After cutting, the cell's DNA repair machinery either joins the cut ends back together in a way that often disrupts the gene knockout, or, if a template DNA sequence is provided, uses it to repair the cut by homologous recombination, incorporating the desired sequence change, gene insertion or correction. Metabolic engineering. Metabolic engineering redesigns the biochemical pathways of microorganisms to redirect metabolism toward the production of desired compounds. This involves inserting genes from other organisms to introduce new enzymatic reactions, overexpressing or downregulating existing genes to redirect flux through pathways, and evolving modified strains in laboratory evolution experiments to improve performance. The production of artemisinin, an anti-malarial drug previously extracted from the wormwood plant, was engineered into yeast by J. Kiesling's laboratory, inserting a dozen genes from various organisms and optimizing their expression to achieve commercially viable yields. The same principles apply to engineering organisms for terraforming, inserting genes for nitrogen fixation into organisms that do not naturally fix nitrogen, or engineering cyanobacteria to tolerate the higher radiation and perchlorate concentrations of the Martian surface. Habitat and infrastructure systems. Closed-loop life support. Water recovery. The ISS water recovery system processes urine, cabin humidity condensate, and water from other sources through multiple purification stages. The urine processor assembly uses a vacuum distillation process. Urine is heated under vacuum, causing water to evaporate at low temperature. The vapor condenses and passes to the water processor assembly, which processes it along with humidity condensate. The water processor assembly uses a series of filtration and chemical treatment steps. A multi-filtration bed removes organic compounds and ions using activated carbon and ion exchange resins. A catalytic oxidation reactor passes the water through a high-temperature catalyst bed in the presence of oxygen, oxidizing any remaining organic compounds to CO2 and water. An iodine biocide system prevents microbial growth. The resulting water meets or exceeds NASA's potable water standards. The overall system achieves approximately 90% water recovery, with the remaining 10% lost in the brine concentrate. Oxygen generation. The oxygen generation assembly electrolyzes water to produce oxygen for breathing and hydrogen as a byproduct. The system uses proton exchange membrane electrolysis cells operating at high current density. The hydrogen byproduct is typically vented overboard on the ISS, but could be used as a fuel or chemical feedstock in a more closed system. Carbon dioxide removal is accomplished by the carbon dioxide removal assembly, which circulates cabin air through beds of zeolite sorbent that absorb CO2. When one bed is saturated, a valve switches airflow to a fresh bed, while the saturated bed is regenerated by heating under vacuum. The desorbed CO2 is either vented or fed to the Sabatier reactor. The SABIDA system reacts CO2 with hydrogen over a ruthenium catalyst at approximately 400 degrees Celsius, producing methane and water. The water is recycled back into the water processing system and ultimately electrolyzed back into oxygen and hydrogen. The methane is currently vented, representing a loss of hydrogen from the system, but in a fully closed system it would be processed further to recover the hydrogen. Information and governance systems. Earth system modeling. General circulation models. General circulation models are the computational engines of climate science. They divide the atmosphere, ocean, and land surface into a three-dimensional grid of cells, typically 50 to 100 kilometers horizontally and dozens of vertical layers, and solve the fundamental equations of fluid dynamics, thermodynamics, and chemistry within each cell and across cell boundaries at regular time steps. The atmospheric component solves the primitive equations, simplified forms of the Navier-Stokes equations of fluid motion, governing wind velocity, temperature, pressure, and humidity. Processes smaller than the grid scale, convective clouds, turbulence, boundary layer mixing, cannot be resolved explicitly and must be represented by parameterization schemes that calculate their aggregate effects based on resolved grid scale variables. The ocean component similarly solves fluid dynamics equations for ocean circulation, temperature, salinity, and density, including representations of sea ice formation and melt, ocean mixing, and biogeochemical cycles. Coupling the atmosphere and ocean requires careful treatment of the exchange of heat, water, momentum, and gases at the ocean surface. Land surface models represent the water and energy balance of the land surface, infiltration of rainfall into soil, evapotranspiration from vegetation, snowpack accumulation and melt, river routing, and soil carbon dynamics. Dynamic vegetation models within the land component simulate the competition between plant functional types, tropical forest, temperate grassland, tundra, etc., in response to changing climate, enabling the simulation of vegetation climate feedbacks. Earth system models add biogeochemical cycling to general circulation models, tracking the movement of carbon, nitrogen, phosphorus, and other elements through the atmosphere, ocean, land, and living organisms. They can simulate the response of ocean carbon uptake to changing temperature and acidification, the release of soil carbon from permafrost as it thaws, and the sensitivity of terrestrial net primary production to CO2 fertilization and temperature change. Artificial intelligence for sustainability, machine learning for energy grid management. Modern electricity grids are extraordinarily complex systems balancing supply and demand in real time across thousands of generators, millions of loads, and extensive transmission infrastructure. The increasing penetration of variable renewable generation, solar and wind, adds forecasting uncertainty and requires faster, more flexible balancing. Reinforcement learning systems, AI agents that learn by interacting with an environment and receiving reward signals, can optimize grid dispatch decisions in real time, balancing cost, reliability, and emissions across a portfolio of generation assets with the complexity and speed impossible for human operators. DeepMind demonstrated that a reinforcement learning system could reduce the energy used for cooling Google's data centers by 40%. Similar approaches are being applied to grid-scale optimization. Short-term forecasting of solar and wind generation using machine learning, integrating satellite imagery, numerical weather prediction, and historical generation data, enables grid operators to anticipate variability and pre-position flexible resources. Transformer-based deep learning models, which excel at capturing long-range temporal dependencies, are achieving forecast accuracy approaching the theoretical limits imposed by atmospheric predictability. AI for materials discovery, the discovery of new materials with desired properties, higher efficiency photovoltaics, better battery cathodes, more effective catalysts, stronger structural materials, has traditionally required laborious experimental synthesis and testing. Machine learning is transforming this process by learning the relationships between material composition, structure, and properties from databases of known materials, and using these relationships to predict the properties of novel, untested compositions. Graph neural networks represent molecules and crystal structures as graphs, atoms as nodes, bonds as edges, and learn to predict properties by propagating information along the graph structure. Models trained on databases like the Materials Project, Flow, and the Cambridge Structural Database can screen millions of hypothetical materials in seconds, identifying candidates for experimental synthesis with predicted properties matching target specifications. Generative AI models, variational autoencoders, generative adversarial networks, diffusion models, can generate novel material structures with specified target properties, going beyond screening existing databases to invent entirely new compositions. This approach is accelerating the discovery of new battery materials, catalysts, and semiconductors at a pace impossible through traditional experimental methods. Transportation and space systems, rocket propulsion, Chemical rocket physics. Chemical rockets produce thrust by expelling propellant at high velocity through a nozzle. The thrust force equals the mass flow rate of propellant multiplied by its exhaust velocity, a relationship derived from Newton's third law. The exhaust velocity is determined by the energy released by the propellant combustion and the efficiency of converting that energy to directed kinetic energy in the nozzle. The specific impulse, exhaust velocity divided by gravitational acceleration, is the standard measure of rocket engine efficiency. A rocket engine with higher specific impulse produces more thrust per unit of propellant mass, enabling a given vehicle to carry more payload or reach higher velocities. Liquid hydrogen liquid oxygen engines achieve specific impulses of 450 seconds, kerosene oxygen engines achieve 340 to 360 seconds, solid rocket motors typically achieve 250 to 280 seconds. In the nozzle, hot high-pressure combustion products expand and accelerate through a convergent-divergent Delaval nozzle. In the convergent section, flow accelerates to sonic velocity at the throat. In the divergent section, supersonic expansion converts thermal energy to kinetic energy, with the exhaust reaching velocities of 3,000 to 4,500 meters per second. Reusable rockets. SpaceX's Falcon 9 achieves first-stage reusability by reigniting its Merlin engines for a series of maneuvers after stage separation. A boost back burn reverses the stage's downrange trajectory. An entry burn reduces velocity to survive atmospheric re-entry, and a landing burn decelerates the stage to zero velocity at the landing pad or drone ship. Grid fins provide aerodynamic control during descent. Deployable landing legs absorb touchdown. The recovered booster is refurbished and reflown, reducing the amortized cost of the rocket structure over multiple flights. SpaceX's Starship takes full reusability further, aiming to make both the Super Heavy booster and the Starship upper stage rapidly reusable, returning the booster to the launch tower to be caught by mechanical arms within minutes of launch, and landing the Starship on its belly using aerodynamic control surfaces before reigniting its engines for a final propulsive landing. Nuclear thermal propulsion. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, typically hydrogen, to very high temperatures, which is then expelled through a nozzle to produce thrust. The reactor heats hydrogen to 2,500 to 3,000 degrees Celsius, far hotter than is achievable by chemical combustion, producing specific impulses of 800 to 1,000 seconds, roughly double that of the best chemical rockets. The reactor core consists of fuel elements, uranium carbide or uranium oxide cermet, through which hydrogen propellant flows, absorbing heat. Control drums with neutron-absorbing and neutron-reflecting sections regulate the chain reaction by rotation. The entire reactor assembly must withstand the extreme thermal and radiation environment while remaining lightweight enough to be practical. Ion propulsion. Ion thrusters accelerate ions electrostatically to produce thrust. In a gridded ion thruster, xenon propellant is ionized by electron bombardment in a discharge chamber. The resulting ions are accelerated through a set of biased grids to exhaust velocities of 20,000 to 80,000 meters per second, 10 to 20 times the exhaust velocity of chemical rockets, producing specific impulses of 2,000 to 8,000 seconds. The thrust of ion thrusters is very small, millinewtons to a few newtons, but their extraordinary efficiency means that a small amount of propellant can produce a large change in velocity over time. Ion thrusters are ideal for long-duration missions where time is available to gradually build up velocity, and have been used on missions including Dawn, Hayabusa, and the commercial geosatellites. In situ resource utilization. Oxygen production from CO2. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, demonstrated on the Perseverance rover the production of oxygen from Martian CO2. The device uses solid oxide electrolysis. CO2 from the Martian atmosphere is pumped into a solid oxide electrolyzer operating at about 800 degrees Celsius. At the cathode, CO2 is reduced to CO and oxygen ions. The oxygen ions migrate through the solid yttrium-stabilized zirconia electrolyte to the anode, where they are oxidized to O2 gas. MOXIE successfully produced oxygen in multiple operational runs on Mars, proving the principle at small scale. Scaling MOXIE to a facility capable of producing the tons of liquid oxygen needed for rocket propellant requires orders of magnitude increases in throughput and the addition of liquefaction and storage systems. The engineering challenges of high-temperature electrochemistry in the Martian environment, extreme cold, low pressure, dust, and radiation, are substantial but tractable. Metal production from regolith. Martian regolith contains approximately 13% iron, 10% aluminum, 6% calcium, and significant silicon and magnesium, plus many other elements in smaller quantities. Producing metals from this regolith for construction and manufacturing requires extractive processes adapted to Martian conditions. Molten oxide electrolysis heats regolith to above its melting point, approximately 1,500 degrees Celsius, forming a molten oxide electrolyte through which current is passed. Oxygen evolves at the anode as a useful byproduct. Metal alloys sink to the cathode and can be tapped off. This process, developed in the context of lunar and Martian ice research, can produce iron, silicon, and other metals from oxide-rich regolith using only electrical energy in the regolith itself. Carbothermal reduction reacts regolith with carbon monoxide, producible from CO2 by the reverse water-gas shift reaction, at high temperature to produce metal oxides and CO2, the CO2 being recycled. Metal oxides are then reduced to metals by further heating with carbon or hydrogen. The integrated picture. Every system and technology described above, from the quantum physics of a solar cell, to the microbiology of a precision fermentation reactor, to the orbital mechanics of a reusable rocket, is part of a single, coherent civilizational project. The photovoltaic effect that powers a rooftop solar panel is the same physics that would power a Martian surface installation. The membrane chemistry of a reverse osmosis plant is the same science that would purify water from Martian ice. The atmospheric modeling that projects Earth's climate decades into the future is the same computational framework that would plan and monitor a Martian atmospheric transformation over centuries. The full technical depth of each system is staggering. Each bullet point in a high-level overview conceals decades of scientific and engineering development, thousands of researchers, and billions of dollars of investment. And yet the overall architecture is coherent: master energy, master materials, master atmosphere, master water, master biology, master information, master space, and in doing so, become a civilization capable of sustaining itself on one world and building life on others. The work is long, the science is deep, the engineering is hard, and it begins, in every case, with the next experiment, the next deployment, the next policy, the next generation of students who will carry it forward. That is how civilizations are built, one system at a time, each one standing on all that came before. What green, regenerative and sustainable systems can be integrated to other planets? This is the culminating technical and philosophical question of our entire conversation, taking everything we have built up about sustainability, terraforming, and planetary systems, and asking precisely which green, regenerative, and sustainable systems can be transplanted, adapted, and evolved for use on other worlds. The answer is comprehensive, technically rich, and deeply interconnected. The integration framework, the transplantation principle. Not every system developed on Earth can be directly transplanted to another planet. Each must be evaluated across 4 dimensions: transferability, how directly the system translates without modification. A solar panel works on Mars with minor adjustments for lower irradiance and dust. A tropical rainforest ecosystem does not transfer at all in its current form. Adaptability, how much engineering, biological modification, or redesign is required. Hydroponic food production transfers readily with adaptation to local gravity, radiation, and resource availability. Conventional agriculture requires complete reimagining. Generativity, whether the system can sustain and reproduce itself using local resources once established, reducing dependence on Earth resupply. This is the defining characteristic of a truly integrated planetary system. Sequentiality, whether the system requires other systems to be in place first. Outdoor agriculture requires a breathable atmosphere. A breathable atmosphere requires centuries of prior biological and chemical terraforming. Sequencing matters enormously. With this framework, every green, regenerative, and sustainable system can be mapped to a phase of planetary development, from the earliest robotic precursor missions through full terraforming and open-air civilization. Part 2, Energy Systems. Solar energy systems. Direct transfer with adaptation. Photovoltaic solar technology transfers to Mars with 3 primary adaptations. First, Mars receives approximately 43% of Earth's solar irradiance at the surface, about 590 watts per square meter at the equator under clear conditions, compared to Earth's 1,000 watts per square meter. Panel arrays must be sized accordingly, requiring roughly 2.3 times the panel area for equivalent output. Second, Martian dust storms, which can engulf the entire planet for weeks to months, dramatically reduce solar input and deposit dust on panel surfaces. The design response involves self-cleaning mechanisms using electrostatic dust removal, applying oscillating electric fields that repel charged dust particles from panel surfaces, combined with robust battery storage to sustain operations through storm periods. Third, the extreme cold of Mars, nighttime temperatures dropping to -80 degrees Celsius at mid-latitudes, requires panel materials and mounting systems designed for thermal cycling far more extreme than any terrestrial environment. Perovskite cells, being solution deposited, are particularly concerning for cold climate durability. Silicon heterojunction cells have demonstrated better performance retention at low temperatures. On Venus, solar energy faces the opposite challenge. The dense cloud cover reduces surface irradiance to about 10% of Earth's, making surface solar power impractical. However, above the cloud layer at 50 to 60 kilometers altitude, where a proposed floating habitat concept exists, solar irradiance is similar to Earth's, making solar power viable for atmospheric installations. On the Moon, 2-week-long lunar nights require either enormous battery storage, nuclear backup power, or installation at polar locations where crater rims receive near-continuous sunlight. The peaks of eternal light near the lunar south pole receive sunlight for over 90% of the year and are priority locations for solar installations. Space-based solar power. For any planet, Space-based solar power, collecting sunlight in orbit and beaming it to the surface via microwave or laser, bypasses atmospheric absorption, dust storms, and day-night cycles entirely. A solar power satellite in a geosynchronous orbit around Mars would beam continuous power to a receiving antenna on the surface below. The technology requires large, lightweight deployable solar arrays, high-efficiency power conversion and transmission systems, and receiving antennas that can convert microwave energy back to electricity with high efficiency. Development of this technology for Earth applications directly enables its use at any planet. Wind energy systems. Martian wind power. Mars has an atmosphere, thin at roughly 0.6% of Earth's surface pressure, but it does have wind, sometimes extreme wind during dust storm season when velocities can reach 100 meters per second. However, the low atmospheric density means that even high wind speeds carry little kinetic energy. Wind power available is proportional to air density, and Martian air density is about 60 times lower than Earth's sea level density. A 100 meter per second Martian wind carries about the same power as a 20 meter per second Earth wind. Turbine designs for Mars require very large rotors to intercept more of the thin air, extremely lightweight construction to minimize structural loads under low gravity, and blade profiles optimized for the low Reynolds number of flow conditions of the thin Martian atmosphere. Autogyro designs and kite-based systems that can operate at high altitude where winds are stronger are under study. Wind power on early Mars is a supplementary rather than primary resource, but becomes increasingly viable as atmospheric pressure grows during terraforming. Atmospheric wind power on terraformed planets. A fully terraformed planet with Earth-like atmospheric pressure and active weather systems becomes fully amenable to conventional wind turbine technology. The entire wind energy toolkit, onshore turbines, offshore floating platforms, airborne wind systems, transfers completely once sufficient atmosphere exists. Geothermal energy systems. Mars geothermal. Mars was volcanically active relatively recently in geological terms. The Tharsis volcanic province shows evidence of activity within the last few 100 million years, and some researchers argue for episodic activity even more recently. Subsurface heat flow, while lower than Earth's, likely supports geothermal gradients sufficient for low-temperature geothermal energy extraction. Enhanced geothermal systems, which inject water into hot rock at depth, circulate it through the rock to absorb heat, and extract the heated water or steam, do not require naturally occurring hydrothermal systems. They require only sufficient subsurface temperature gradient and the ability to drill and fracture rock at depth. On Mars, eggs could provide continuous baseload power independent of sunlight and wind, representing a highly valuable complement to solar. The drilling technology and thermal cycle engineering transfer directly from Earth applications. Io and Europa geothermal. Jupiter's moon Io is the most volcanically active body in the solar system, heated by tidal forces from Jupiter's immense gravity. Europa, beneath its ice shell, has a liquid water ocean kept warm by similar tidal heating. For any future installation on or near these moons, geothermal energy is abundant and essentially unlimited, a profoundly different energy context from the inner solar system. Nuclear energy for planetary applications. Kilopower, NASA's small fission reactor design using uranium-235 fuel and Stirling engine power conversion, is specifically designed for planetary surface deployment. A single kilopower unit produces 1 to 10 kilowatts of electrical power from a package small and light enough to land on another world. Arrays of kilopower units can provide the tens to hundreds of kilowatts needed for early human surface operations, functioning completely independently of sunlight and weather. This technology is the direct application of small modular reactor development to planetary power. Closed-loop material systems. Water recycling and recovery. Hermetically closed water cycles. The water recycling systems developed for the ISS, urine processing, humidity condensate recovery, catalytic oxidation purification, form the foundation of water management in any early planetary habitat. The engineering challenge for Mars is adapting these systems to operate in Martian gravity, roughly 38% of Earth's, which affects fluid dynamics, phase separation, and pump design throughout the system. On the Moon, water ice confirmed and permanently shadowed craters near the poles can be mined, melted, purified, and introduced into a habitat's water cycle. The water then cycles continuously through use, recovery, and purification, with makeup from ice mining compensating for any losses. This represents the integration of in-situ resource extraction with closed-loop recycling, a model that would apply equally to any icy body in the outer solar system. Atmospheric water recovery. In a pressurized habitat with crew breathing and perspiring, moisture accumulates in the atmosphere and must be actively removed and recycled. Dehumidification systems condense this water vapor and feed it into the water recovery system. In a mature habitat with a large crew, atmospheric moisture recovery contributes substantially to total water supply, essentially harvesting water from the crew's own metabolism and respiration. For surface operations outside the habitat, suit life support systems must similarly recover exhaled moisture. Absorption beds of lithium chloride or silica gel capture moisture from exhaled air, and periodic regeneration by heating releases the collected water for recycling within the suit's life support system. Nutrient cycling systems. Composting and biological nutrient recovery. Any long-duration planetary habitat generates organic waste, human feces, Food preparation waste, dead plant material from food production. Rather than treating this as a disposal problem, a regenerative system processes all organic waste biologically to recover nutrients and organic matter for return to food production. Vermicomposting, using earthworms and associated soil microbiota to process organic waste, is particularly well suited to enclosed habitats because it operates at low temperatures, produces no offensive gases if properly managed, and delivers a highly fertile finished compost within weeks. The earthworms themselves, along with the microbial communities they host, are key components of the closed biological loop. Urine diversion and separate treatment allows recovery of nitrogen, primarily as urea, and phosphorus, primarily as struvite, before urine enters the general wastewater stream. These recovered nutrients are high-value fertilizers for the food production system, closing the nutrient loop between human metabolism and food production in a way that conventional wastewater treatment does not achieve. Struvite precipitation, adding magnesium ions to phosphorus-rich wastewater to precipitate magnesium ammonium phosphate, recovers phosphorus in a slow-release crystalline form directly usable as fertilizer. This is particularly important because phosphorus, unlike nitrogen, cannot be fixed from the atmosphere. Every phosphorus atom used in food production must be recovered and recycled in a closed planetary system. Biochar production and application. Pyrolysis of organic waste, food scraps, plant residues, packaging materials, at moderate temperatures in the absence of oxygen produces biochar, a highly porous, stable form of carbon. Biochar incorporated into growing media dramatically improves water retention, nutrient holding capacity, and microbial habitat. It is stable for centuries to millennia, representing a long-term carbon store within the habitat's biological system. In a planetary habitat, biochar produced from waste biomass and incorporated into the food production growing media creates a virtuous cycle. Waste becomes a soil amendment that improves food production efficiency, which reduces the waste generated per unit of food produced. Atmospheric and climate systems. Atmospheric processing for early habitats. CO2 scrubbing and oxygen generation. Early planetary habitats require active atmospheric management to maintain breathable conditions. CO2 exhaled by crew accumulates rapidly in a sealed volume. A crew of 6 exhales approximately 6 kilograms of CO2 per day. Zeolite sorbent beds or amine scrubbers continuously remove CO2 from habitat air. The captured CO2 is the feedstock for oxygen regeneration via the Sabatier reaction and water electrolysis cycle described earlier. Alternatively, on Mars where atmospheric CO2 is abundant, solid oxide electrolysis can produce oxygen directly from the Martian atmosphere. The MOXIE approach, with CO byproduct either vented, used as a fuel, or processed further. Algae bioreactors offer a biological alternative to electrolytic oxygen production. Photosynthetic algae, particularly fast-growing strains of chlorella and spirulina, consume CO2 and produce oxygen through photosynthesis, driven by LED lighting. A bioreactor of sufficient volume can maintain the atmospheric CO2-oxygen balance for a small crew while simultaneously producing biomass that serves as a supplementary food source. The algae thus perform triple duty: atmospheric regulation, food production, and organic waste processing. Greenhouse atmospheric management. As habitats grow into larger pressurized greenhouse structures, perhaps covering craters or valleys with transparent domes, atmospheric management becomes more complex and the biological contribution more significant. A sufficiently large enclosed ecosystem, with enough photosynthetic biomass, can maintain its own atmospheric balance without active electrolytic intervention. Designing the species composition, density, and management of such an ecosystem to achieve stable atmospheric balance is a profound bioengineering challenge, and a scaled-down version of the planetary atmospheric engineering required for full terraforming. Planetary atmospheric engineering. Greenhouse gas generation and release. The first phase of Martian terraforming involves warming the planet by thickening its atmosphere with greenhouse gases. The most studied approach involves producing potent synthetic greenhouse gases, perfluorocarbons such as perfluoromethane, CF4, perfluoroethane, C2F6, and sulfur hexafluoride, SF6, from Martian atmospheric and surface resources, and releasing them continuously over centuries. These gases are particularly well suited for Martian greenhouse warming because they absorb infrared radiation in spectral windows where CO2 does not, augmenting the warming effect of the native CO2 atmosphere. They are chemically inert and not metabolized by biology, persisting in the atmosphere for thousands to tens of thousands of years. They can be manufactured from fluorine-bearing minerals in Martian regolith. Fluorapatite, for example, using electrochemical processes powered by nuclear or solar energy. Calculations suggest that establishing a manufacturing capacity of a few kilograms per second of these gases, achievable with a modest but sustained industrial effort, could raise Martian temperatures by 20 to 30 degrees Celsius over a century, beginning to unlock CO2 in water ice reservoirs and initiating a positive feedback loop of further warming. Polar ice sublimation. Mars's southern polar cap contains a permanent layer of CO2 ice overlying water ice. If the CO2 ice could be sublimated, converted directly from solid to gas, it would add substantially to the atmospheric pressure and greenhouse effect. One proposed mechanism involves spreading dark material, carbon black, dark mineral dust, on the polar cap surface, reducing its reflectivity and allowing it to absorb more solar heat. Space-based orbital mirrors, large, thin reflective films in a sun-synchronous orbit positioned to redirect sunlight onto the polar regions, represent a more controllable and powerful approach. Mirrors with a reflective area of hundreds of thousands of square kilometers could concentrate sufficient additional solar energy on the poles to drive rapid sublimation. The manufacturing of such mirrors from asteroidal or lunar materials, avoiding the enormous cost of launching them from Earth, is a key enabling technology. Food and biological systems, controlled environment food production, hermetically sealed greenhouse systems. The first food production systems on any other planet will be hermetically sealed controlled environment agriculture installations, essentially sophisticated vertical farms adapted for planetary surface conditions. These systems integrate LED or solar lighting, hydroponic or aeroponic growing systems, closed-loop nutrient solution management, atmospheric control, and biological pest management into a self-contained food production unit. On Mars, natural sunlight, filtered through transparent dome material that blocks harmful UV and high-energy particles, supplements or replaces LED lighting during daytime hours, reducing electrical energy demand. Thin-film fluoropolymer materials like ETF are strong, transparent, and highly resistant to UV degradation, making them candidates for dome glazing. Crop selection for early planetary food production prioritizes caloric density, nutritional completeness, growth rate, and space efficiency. Calorie staples, potatoes, sweet potatoes, soybeans, wheat, provide bulk energy. Leafy greens and herbs provide micronutrients and psychological variety. Algae and duckweed provide high-protein supplementary nutrition in very small footprints. Strawberries and tomatoes provide psychologically important fresh produce with relatively modest resource demands. Aquaponics integration. Aquaponics integrates fish cultivation with plant production in a mutually beneficial closed system. Fish produce waste ammonia that beneficial nitrifying bacteria, Nitrosomonas and Nitrobacter species, convert first to nitrite and then to nitrate. Plants absorb this nitrate as fertilizer while simultaneously purifying the water for the fish. The integrated system produces both protein from fish and calories and nutrients from plants, while using less water and producing less waste than either system alone. Tilapia and catfish are the most studied species for aquaponic systems, both tolerant of variable water quality, fast-growing, and efficient converters of feed to flesh. In a planetary habitat, insects or algae grown from organic waste can replace conventional fish feed, closing the organic loop within the food production system. Duckweed, tiny floating aquatic plants that cover water surfaces and grow with extraordinary speed, can be integrated into aquaponic systems as both a water purifier and a high-protein food crop. Duckweed contains 25 to 45% protein by dry weight, can double its biomass in 24 to 48 hours, and extracts nitrogen and phosphorus from water with high efficiency. Biological terraforming systems. Pioneer organism sequences. Biological terraforming would proceed through a carefully designed succession of increasingly complex organisms, each modifying the environment to make it more hospitable for its successors, precisely the process of ecological succession that follows a volcanic eruption or glacial retreat on Earth. Stage 1. Camelothotrophs. The first organisms deployed to a planetary surface would be camelothotrophs, microorganisms that derive energy not from sunlight or organic carbon, but from inorganic chemical reactions. Certain bacteria oxidize iron, sulfur, hydrogen, or ammonia to obtain energy, fixing CO2 as their carbon source. On Mars, hydrogen-oxidizing bacteria could use H2 from subsurface volcanic sources and atmospheric CO2 to grow, producing organic matter from entirely inorganic materials. Sulfur-oxidizing bacteria could exploit the sulfate-rich Martian regolith. These organisms would begin the process of producing the first organic matter, the foundation of soil, on the planetary surface. Stage 2. Photosynthetic pioneers. Once the first thin films of organic matter and microbial biomass exist, photosynthetic pioneers, primarily cyanobacteria and extremophile algae, can be introduced. Cyanobacteria are among the most environmentally tolerant organisms on Earth. Crocoxidiopsis species survive extreme desiccation, intense UV radiation, high salinity, and temperature extremes from -20 to +60 degrees Celsius. They photosynthesize using CO2, fix atmospheric nitrogen, and produce oxygen. They were the organisms responsible for the Great Oxidation event on Earth 2.4 billion years ago. They can do the same on Mars, far faster. Cyanobacteria would be the primary oxygen generators of biological terraforming, gradually shifting the atmospheric composition from near pure CO2 toward an oxygen-containing mixture over thousands to tens of thousands of years, with the timeline compressible by genetic engineering, including engineering enhanced radiation tolerance, perchlorate reduction pathways, and high-altitude freezing tolerance. Stage 3. Soil building consortia. As cyanobacterial mats accumulate, fungi, archaea, and other bacteria can colonize the organic layer, beginning the process of true soil formation. Mycorrhizal fungi, which form symbiotic associations with plant roots, must be established before vascular plants can thrive. Nitrogen-fixing bacteria, Rhizobium, Azotobacter, and others, must be present to supply fixed nitrogen for plant growth. Decomposers that break down dead organic matter must close the nutrient cycle. Designing these microbial consortia, selecting species, engineering their interactions, testing their performance in Mars analog environments, is a profound challenge in synthetic ecology. The research base is developing on Earth through microbiome science, ecological restoration, and synthetic biology. Stage 4, vascular plant introduction. Once soil organic matter reaches sufficient levels and atmospheric oxygen and pressure begin to rise with atmospheric warming and biological oxygen production, primitive vascular plants can be introduced to low-altitude, sheltered environments, crater floors, lava tubes, south-facing equatorial slopes, where conditions are marginally more favorable. Mosses, lichens, and ferns, which tolerate low nutrient soils, temperature extremes, and high radiation, would be the initial vascular colonizers. Hardy grasses and legumes would follow, with legumes providing crucial biological nitrogen fixation and grass roots providing the mechanical and biological processes that build deeper soil structure. Stage 5, engineered ecosystem assembly. As conditions approach Earth-like, the full toolkit of ecological restoration science, species selection, keystone species introduction, trophic structure design, disturbance management, becomes applicable. This is where the deep knowledge base of Earth ecosystem restoration science directly enables planetary ecosystem construction. Genetic engineering for planetary organisms. Every stage of biological terraforming benefits from genetic engineering of pioneer organisms. Key engineering targets include radiation resistance. The bacterium Deinococcus radiodurans can survive radiation doses thousands of times lethal to humans, using extraordinarily efficient DNA repair mechanisms. The genes encoding these repair systems, RECA, recombinases, specific exonucleases, can be introduced into cyanobacteria and other pioneer organisms to extend their radiation tolerance to the Martian surface environment. Perchlorate tolerance and reduction. Martian regolith contains 0.5 to 1% perchlorate, far higher than concentrations toxic to most Earth organisms. However, perchlorate-reducing bacteria, Dechloromonas and Azospirus species, use perchlorate as a terminal electron acceptor in anaerobic respiration, converting it to chloride and oxygen. Engineering these pathways into pioneer organisms allows them to not only tolerate perchlorate, but actively detoxify the soil. Cold tolerance. Antifreeze proteins from Arctic fish, insects, and plants prevent ice crystal formation in cells at sub-zero temperatures. Engineering these proteins into cyanobacteria and crop plants extends their operational temperature range. Psychrophilic, cold-loving, bacteria from Antarctic environments provide a further source of cold adaptation genes. Enhanced nitrogen fixation. The nitrogenase enzyme complex responsible for biological nitrogen fixation is energetically expensive and sensitive to oxygen. Engineering more efficient nitrogenase variants, or transferring nitrogen fixation capacity to organisms that do not naturally possess it, could dramatically accelerate the nitrogen enrichment of a planetary atmosphere and soil. Photosynthetic efficiency enhancement. Natural photosynthesis converts only about 1 to 3% of incident solar energy to chemical energy, a fraction of the thermodynamic limit. Engineering organisms with optimized light harvesting complexes, more efficient carbon fixation enzymes, and reduced photorespiration could significantly increase the rate of oxygen production and organic matter accumulation, accelerating biological terraforming. Habitat and construction systems. Regenerative building materials. Mycelium composites. Mycelium, the thread-like vegetative body of fungi, can bind agricultural or mineral substrates into rigid, lightweight, thermally insulating composite materials. A mold is filled with substrate, hemp herds, crop residues, or on another planet, fibrous mineral material, inoculated with fungal spores, and allowed to grow for several days in controlled humidity and temperature. The mycelium threads grow through and around the substrate particles, binding them into a solid mass. Heat killing the mycelium arrests growth and stabilizes the material. On a planet with established biological systems producing plant biomass, mycelium composites could be grown from local organic material into structural panels, insulation blocks, and custom-shaped components. The only inputs are substrate, fungal inoculant, water, and controlled environment conditions, all available in a developed planetary habitat. Regolith-based construction. Before biological systems are established, construction must rely entirely on mineral materials. Martian regolith can be sintered, heated to near its melting point without full melting, causing surface bonds to form between particles, into rigid bricks using concentrated solar heat or microwave energy. The basaltic composition of much Martian regolith produces sintered material with compressive strength comparable to weak concrete. Sulfur concrete, mixing molten sulfur with regolith aggregate, produces a structural material without requiring water, which is scarce in early surface operations. Martian regolith contains several percent sulfate minerals, extracting and purifying sulfur from these, then mixing with regolith aggregate and casting in molds, produces blocks with compressive strength of 30 to 40 megapascals, comparable to conventional concrete, that are also resistant to acid and salt attack. 3D printing of regolith, using robotic systems that deposit and sinter or bind regolith layer by layer, enables the construction of complex structures including vaulted arches, domes, and interlocking components that would be impractical with block construction. NASA, ESA, and private companies have demonstrated regolith 3D printing using lunar and Martian simulants. Living architecture. Living architecture, building systems that incorporate living organisms as structural, functional, or environmental components, represents a longer-term integration of biology and construction. Structural mycelium panels that continue growing and self-repairing, living walls of photosynthetic organisms that contribute to atmospheric oxygen production, and root systems engineered to bind and stabilize oil structures are all concepts under early development. In a mature planetary habitat, the boundary between building and ecosystem begins to dissolve. A habitat designed as a living system, in which structural materials, atmospheric management, food production, water cycling, and waste processing are all integrated functions of a single biological architecture, represents the ultimate expression of regenerative design applied to planetary settlement, information and ecological monitoring systems. Planetary sensor networks. A terraforming planet requires continuous, comprehensive environmental monitoring across its entire surface and throughout its atmosphere and subsurface, tracking the progress of atmospheric changes, biological establishment, water cycle development, temperature distribution, and geological activity. This requires networks of surface weather stations, atmospheric profiling balloons, orbital remote sensing satellites, seismic networks, and biological monitoring systems, all integrated into a comprehensive planetary information system. The design of such networks draws directly on Earth's environmental monitoring infrastructure, the satellite constellations, surface station networks, ocean buoy arrays, and atmospheric profiling systems that provide the data for Earth system modeling. The difference is scale. A planetary monitoring network must function autonomously for centuries, self-repairing and upgrading, without the constant maintenance that Earth systems receive. Ecological modeling for planetary systems. The computational models used to design, plan, and manage biological terraforming are extensions of Earth's ecological modeling frameworks. Population dynamics models, species distribution models, nutrient cycle models, and ecosystem metabolism models, all developed in the context of Earth ecology and conservation, provide a mathematical foundation for predicting how a designed ecosystem will develop on another world. The challenge is that planetary ecosystems will encounter conditions and interactions not represented in Earth's ecological history. Novel evolutionary pressures, engineered organisms with non-natural capabilities, and physical environments with no Earth analogs will produce dynamics that cannot be predicted by extrapolating from Earth models alone. Extensive experimentation in enclosed Mars analog environments on Earth and eventually in enclosed habitats on Mars itself is essential for developing and validating these models. The integration map. Phase-by-phase system integration, bringing all of these systems together into a coherent sequence, produces a roadmap of system integration across the phases of planetary development. Robotic precursor phase, year 020. Nuclear killer power units provide baseload electricity. Robotic ice roof systems produce oxygen, water, and construction materials from local resources. Automated construction robots build initial habitat structures from sintered regolith and sulfur concrete. Environmental monitoring networks are established across the surface and in orbit. Pioneer microbial cultures are tested in enclosed Mars analog chambers. Early human presence phase, years 1050. Crews of 6 to 50 inhabit pressurized habitats with fully closed water recycling, atmospheric management, and initial closed environment food production. Solar arrays and nuclear reactors provide power. Algae bioreactors and hydroponic systems produce supplementary food. Composting and nutrient recovery systems close the biological loop within the habitat. Pioneer organisms are introduced to sheltered surface locations and enclosed test plots. Expanding settlement phase, years 3100. Habitats grow to support hundreds then thousands of inhabitants. Larger pressurized greenhouse structures under transparent domes provide significant food production. Aquaponic systems produce fish and plant protein. Biological pioneer organisms establish in surface enclaves. Greenhouse gas manufacturing begins planetary atmospheric warming. Water ice mining and recycling supports growing populations. Biological terraforming phase, years 5500. Atmospheric warming unlocks CO2 in water ice reservoirs. Atmospheric pressure begins to rise. Pioneer cyanobacteria spread across equatorial regions. Oxygen content begins rising from essentially zero. Soil formation begins in biological enclaves. Chemical and biological nitrogen fixation increases atmospheric nitrogen. Enclosed habitats grow larger as atmospheric pressure approaches levels where only oxygen supplementation is needed. Advanced terraforming phase, years 200-1000 plus. Atmospheric pressure reaches levels tolerable with supplemental oxygen equipment. Primitive vascular plants establish outdoors in the most favorable locations. Complex ecological communities develop in enclosed biomes. Engineered ecosystems begin functioning as self-sustaining units. Orbital mirrors and industrial greenhouse gas production continue planetary warming. Rivers and lakes form as surface water becomes stable. Mature terraformed phase, years 500 to 10,000 plus. A breathable atmosphere with Earth-like oxygen and nitrogen content exists across the planet. Open-air agriculture becomes possible. Complex multi-trophic ecosystems function across continental scales. Weather systems, rainfall, and river networks operate. Human civilization on the planet becomes self-sustaining and eventually independent of Earth resupply. The full suite of Earth's sustainable agriculture, renewable energy, and circular economy systems operates in an open planetary environment. The synthesis. What this tells us about life itself, the deepest insight from mapping green, regenerative, and sustainable systems onto planetary integration, is what it reveals about the nature of life and sustainability as universal principles, rather than Earth-specific phenomena. Life is fundamentally a system for capturing energy from a gradient, sunlight, chemical disequilibrium, and using it to maintain order, cycle materials, and replicate itself against the tendency of entropy to disperse structure. Every sustainable system, biological or technological, embodies this same principle: capture energy, cycle materials, maintain complexity. A solar panel capturing photons and converting them to electricity is doing, at a technological level, what a chlorophyll molecule does in a leaf. A composting system cycling organic waste back to soil nutrients is doing, at a managed level, what a forest floor's decomposer community does spontaneously. A closed-loop water recycling system is doing, at a mechanical level, what the planetary hydrological cycle does at continental scale. The green, regenerative, and sustainable systems developed on Earth are not a collection of unrelated technologies and practices. They are a suite of solutions to the universal challenge of maintaining complex ordered systems in a universe governed by entropy, solutions discovered through billions of years of biological evolution and several centuries of technological development. These solutions are portable because the challenge is universal. Any planet with an energy source and raw materials can, in principle, support the same fundamental processes: energy capture, material cycling, biological complexity, conscious intelligence. The specific implementations differ: a Martian solar panel, a cyanobacterial soil builder, a regolith water extractor, but the underlying principles are identical to those operating in an Earth forest, a circular economy factory, and a renewable energy grid. In this sense, terraforming is not humanity imposing itself on an alien world. It is life extending its fundamental processes, energy capture, material cycling, ecological complexity, to a new substrate. And the green, regenerative, and sustainable systems developed on Earth are not just tools for fixing Earth's environmental problems. They are the portable, universal toolkit of life itself, ready to be carried to any world where the conditions for their operation can be established. The work begins here, with this planet, with these systems, with this generation, and it extends, in principle, as far as life itself can reach. How can we integrate green, regenerative and sustainable systems to our society to be able to terraform other planets? This is the master integration question, the one that ties every thread of our entire conversation into a single, actionable civilizational strategy. The answer requires thinking simultaneously across personal behavior, community design, national policy, industrial transformation, biological systems, technological development, and cosmic ambition. Here is the most comprehensive treatment possible. The foundational principle: why integration comes before terraforming. Every conversation we have had arrives at the same conclusion from a different direction. You cannot terraform another planet with a civilization that has not first learned to sustain itself. The integration of green, regenerative, and sustainable systems into society is not preparatory work that precedes the real task. It is the first phase of the real task, the phase conducted on the only planet where we already have infrastructure, biology, atmosphere, and institutional memory. The integration challenge has three distinct dimensions that must be pursued simultaneously: technical integration, embedding sustainable technologies into every sector of the economy so deeply that unsustainable alternatives become obsolete, not merely regulated; social integration, transforming the values, behaviors, institutions, and cultural norms of human civilization so that sustainability is not an external constraint but an internal motivation; systemic integration, designing the connections between systems so that the output of one becomes the input of another, eliminating waste at every level and creating the circular, self-reinforcing flows that characterize both healthy ecosystems and healthy civilizations. When all three dimensions are achieved simultaneously, the result is not just a sustainable society. It is a society that has mastered the art of managing complex planetary systems, and is therefore capable of extending that mastery to other worlds. Integrating energy systems, electrifying everything. The first and most urgent integration task is the complete electrification of energy consumption across every sector of society, powered by renewable and nuclear sources. This is not merely a technical challenge, it is a systems integration challenge of the highest order. The electricity grid is civilization's nervous system. The electricity grid must be transformed from a one-way delivery system, power plants pushing electricity to passive consumers, into a dynamic, bidirectional network that integrates distributed generation, flexible demand, and massive storage into a coherent whole. Every rooftop solar panel, every EV battery, every industrial heat pump becomes both a consumer and a potential contributor to this network. Integrating this into society means embedding energy intelligence into every building, every vehicle, every industrial process, and every appliance. Smart meters that communicate consumption patterns in real time, building management systems that automatically shift loads to periods of high renewable generation, vehicle-to-grid charging systems that use EV batteries as distributed storage. All of these represent the weaving of energy sustainability into the fabric of daily life, rather than its confinement to power plants and utility companies. The terraforming connection is direct and profound. A civilization that has designed its entire energy system as a dynamic, self-balancing, distributed network has demonstrated mastery of complex systems management at continental scale. The same systems thinking, the same control architecture, the same resilience engineering that manages a continental renewable grid is what would manage the power systems of a planetary terraforming operation. Industrial decarbonization is systems integration. The hardest sectors to decarbonize, steel, cement, chemicals, shipping, aviation, require not just technology substitution but systems redesign. Green hydrogen produced by electrolysis replaces coking coal and steel production through direct reduction of iron ore, but integrating green hydrogen into steel production means redesigning the entire supply chain. Electrolysis facilities co-located with renewable energy sources, hydrogen storage and distribution systems, modified blast furnace or electric arc furnace designs, and new logistics for hydrogen delivery to steel mills. Each of these integration challenges is simultaneously a capability development for terraforming. Hydrogen production, storage, and distribution at industrial scale on Earth is the direct precursor to hydrogen fuel production and management on Mars. Industrial scale electrolysis is the precursor to the oxygen production systems that would support human life on another planet. High temperature industrial processes using renewable electricity are the precursors to the mineral processing and metal extraction systems that would operate on a planetary surface. Energy poverty as a terraforming prerequisite. A civilization with 2 billion people lacking reliable electricity access cannot sustain the global cooperation and institutional stability that terraforming requires. Integrating sustainable energy systems into society therefore means extending them to every human being on Earth through distributed solar microgrids, small-scale hydropower, community wind, and efficient biomass systems adapted to local resources. This is not charity. It is the construction of the human capital, educated, healthy, connected, economically productive people that a terraforming civilization requires. Every person lifted out of energy poverty is a potential scientist, engineer, farmer, or citizen whose contribution to the collective project becomes possible only when their basic needs are reliably met. Integrating circular material systems. Designing waste out of society. The integration of circular material systems into society requires intervention at every stage of the material life cycle, from the design of products, to the management of manufacturing processes, to the collection and processing of end-of-life materials, to the creation of markets for recovered materials. Product design is civilizational infrastructure. The single most powerful point of intervention in the material cycle is product design. A product designed for disassembly, with labeled materials, reversible fasteners, modular components, and standardized interfaces, costs almost the same to design and manufacture as one designed without these features, but it costs a fraction as much to recover, repair, and recycle at end of life. Integrating design for circularity into society means embedding it in education, engineering and design schools teaching circular principles as standard practice, not elective additions. It means embedding it in regulation, mandatory recyclability requirements, material disclosure rules, and repairability standards that make circular design the path of least resistance for manufacturers. It means embedding it in procurement, governments and large corporations using their purchasing power to demand circular products, creating the market pull that signals to industry that circular design is worth the investment. The terraforming connection runs through manufacturing capability. A civilization that has mastered circular product design has developed the engineering culture, the material science knowledge, and the manufacturing precision needed to design the closed-loop systems of a planetary habitat, where every component must be recoverable, every material must be recyclable, and nothing can be discarded. Urban mining is industrial policy. The metals, polymers, rare earth elements, and other materials embedded in society's existing stock of products represent an enormous secondary resource base, an urban mine that grows richer every year as more products reach end of life. Integrating urban mining into society's industrial system means building the collection infrastructure, sorting technology, processing capacity, and material markets to recover these resources at scale. Integrating this into daily life means making return of end-of-life products as easy and rewarding as buying new ones. Take-back schemes with meaningful incentives, deposits on electronics, rechargeable batteries, and durable goods that are refunded upon return, align individual behavior with systemic material recovery, extended producer responsibility policies that require manufacturers to fund and manage end-of-life recovery, align corporate incentives with circular material flows. The result, over decades, is a society in which the mining of virgin materials is increasingly replaced by the recovery of secondary materials, reducing environmental impact, reducing supply chain vulnerability, and building the industrial capability for in situ resource utilization on other planets. The digital material passport system, integrating circular material systems at scale, requires knowing what everything is made of. A comprehensive digital material passport system, in which every product carries a digital record of its material composition, manufacturing history, and disassembly instructions, enables intelligent sorting and recovery that is impossible with anonymous products. Implementing this at societal scale requires standards bodies developing universal material identification systems, manufacturers embedding identification tags in products at manufacture, waste management systems equipped to read these tags and direct materials accordingly, and regulatory frameworks requiring disclosure and traceability. The result is a material economy with full visibility, where every atom can be tracked from extraction through use to recovery. That is also the information architecture needed to manage material flows in a planetary habitat, integrating food and biological systems, transforming agriculture from extraction to regeneration. The integration of regenerative and sustainable food systems into society is perhaps the most complex integration challenge of all, because food production is simultaneously an economic activity, a cultural practice, an ecological process, and a political system, and because the transition from extractive to regenerative agriculture requires changing all of these simultaneously. Soil as civilizational foundation. The integration begins with soil, the living foundation of terrestrial food production. Integrating soil health into society means making it visible, valued, and protected at every level of the food system. At the farm level, soil health integration means supporting farmers in the transition to regenerative practices, cover cropping, reduced tillage, composting, integrated crop livestock systems, agroforestry, through training, financial support for transition costs, and markets that reward soil building practices. Carbon markets that pay farmers for soil carbon sequestration create an economic incentive aligned with ecological outcomes. At the policy level, soil health integration means agricultural subsidy systems that reward outcomes, soil organic matter, biodiversity, water quality, rather than inputs or yields. Soil mapping and monitoring programs that track national soil health over time make progress visible and create accountability. Land use planning systems that protect the most productive soils from urban development treat topsoil as the irreplaceable national asset it is. At the cultural level, soil health integration means embedding understanding of the living soil in education from primary school onward. A generation that understands that a handful of healthy soil contains more organisms than there are humans on Earth is a generation that will protect it. The terraforming connection is foundational. Building soil on another planet, converting sterile mineral regolith into living, fertile growing medium, requires the deepest possible understanding of soil formation processes, soil microbiome ecology, and the interactions between plants, fungi, bacteria, and mineral substrates. Every regenerative farmer building soil health on Earth is conducting the research that terraforming agriculture will depend on. Integrating food production into urban systems. Cities are the largest concentrations of food consumption and food waste, and increasingly, of food production. Integrating sustainable food systems into urban society means designing cities as food-producing systems rather than purely food-consuming ones. Urban agriculture in its many forms, rooftop gardens, community allotments, vertical farms, school gardens, urban orchards, edible street planting, serves multiple integration functions simultaneously. It produces food locally, reducing transport emissions and supply chain vulnerability. It builds urban residents' connection to an understanding of food production. It provides green infrastructure that manages storm water, reduces urban heat, and supports biodiversity. It creates community spaces that build social cohesion. Vertical farming integrated into commercial and residential buildings represents the deepest form of urban food integration. Buildings that produce food as a core function alongside shelter and work. The waste heat from commercial refrigeration can heat growing spaces. Gray water can irrigate hydroponic systems. CO2 from building occupants can be captured and fed to plants. The building becomes a metabolism, cycling energy and materials through multiple uses before they leave the system. This urban food integration model is a direct prototype for planetary habitat food production. The fully integrated building as food system is a scaled-down version of the habitat as closed ecosystem that sustains planetary settlers. The protein transition. Integrating sustainable protein systems into society requires simultaneously reducing demand for resource-intensive animal proteins and scaling up supply of sustainable alternatives. This is as much a cultural and culinary challenge as a technical one. The cultural integration means embedding plant-rich eating in food culture through school meals that normalize diverse plant proteins, food labeling that makes environmental impact visible, public health messaging that aligns dietary health advice with environmental outcomes, and support for chefs and food businesses that make plant-based eating delicious and culturally resonant. The technical integration means scaling precision fermentation, cultivated meat, and plant protein processing to the point where sustainable proteins are cheaper, tastier, and more accessible than conventional animal proteins, removing the cost and convenience barriers that currently make the dietary transition difficult for most people. This requires sustained public investment in food technology alongside the private investment already flowing into the sector. As the protein transition proceeds and terrestrial animal agriculture shrinks, the land freed up, potentially hundreds of millions of hectares globally, becomes available for ecosystem restoration, carbon sequestration, and biodiversity recovery. The dietary transition thus amplifies every other sustainability integration through its land use implications, integrating ecological and biological systems, restoring the living foundation. The integration of ecological and biological systems into society means reversing the long trend of treating natural systems as external to the economy, as either as sources to extract or obstacles to development, and recognizing them as infrastructure that must be maintained, restored, and invested in. Biodiversity as infrastructure. Integrating biodiversity into society means treating it as infrastructure in the most literal sense, accounting for it in national balance sheets, protecting it in land use planning, investing in its restoration through public spending, and managing it with the same institutional seriousness as roads, power grids, and water systems. The tools for this integration are developing rapidly. Natural capital accounting frameworks, being adopted by a growing number of national governments, incorporate the value of ecosystems into economic measurement alongside manufactured capital. Biodiversity net gain requirements in planning law require development to leave biodiversity better than it found it, creating mandatory investment in ecological restoration as a condition of economic development. Payment for ecosystem services schemes compensate landowners for managing land in ways that provide clean water, flood protection, carbon storage, and biodiversity. The terraforming connection is again foundational. The biodiversity of Earth's biosphere is the gene library from which any new biosphere must be assembled. Every species lost is a potential tool for building a planetary ecosystem, gone permanently. Preserving and studying Earth's biodiversity is simultaneously the most urgent conservation priority and the most important research program for planetary biology. Rewilding as ecological engineering. Rewilding, restoring natural processes and species assemblages to degraded landscapes, allowing ecosystems to self-organize and recover, is the most powerful and cost-effective ecological restoration approach known. By reintroducing keystone species, wolves, beavers, large herbivores, apex predators, rewilding triggers cascading ecological recovery that transforms barren or degraded landscapes into complex, functioning ecosystems. Integrating rewilding into society means creating the large, connected protected areas that allow natural processes to operate at landscape scale, supporting the reintroduction of missing species, and managing the human-wildlife interface so that people and recovering wildlife can coexist. This requires rural community engagement and economic support. Rewilding must benefit the people who live alongside it, not simply be imposed on them. The scientific and practical knowledge accumulated in rewilding projects, how pioneer species establish, how trophic cascades restructure ecosystems, how soil builds under recovering vegetation, how water cycles change as landscapes recover, is exactly the knowledge needed to design the ecological succession sequences for biological terraforming. The microbiome revolution. The scientific revolution in understanding microbiomes, the communities of bacteria, archaea, fungi, and viruses that inhabit every environment and every organism, is one of the most significant biological developments of the early 21st century. It is revealing that the health of soils, ecosystems, and human beings is fundamentally a microbiome health question, and that sustainable management of these systems requires understanding and stewarding their microbial foundations. Integrating microbiome science into society means incorporating it into agricultural practice, managing soil microbiomes as a primary agricultural resource rather than destroying them with synthetic chemicals. It means incorporating it into medicine, understanding the human gut microbiome as a critical health determinant and managing antibiotics to protect rather than destroy it. It means incorporating it into ecological restoration, designing microbial inoculants that accelerate ecosystem recovery. This microbiome revolution has the most direct possible relevance to terraforming. Building soil on another planet is fundamentally a microbiome engineering challenge. Designing pioneer ecosystems for a planetary surface is a microbiome design challenge. Every advance in understanding how microbial communities assemble, function, and interact with their physical environment on Earth is advanced toward the biological engineering of another world. Integrating governance and institutional systems. Building the institutions of civilizational continuity. The integration of sustainable governance into society is in many ways the hardest integration challenge, because it requires changing not just technologies or practices, but the fundamental operating logic of political and economic institutions that have been built around short-term incentives and national boundaries. Long-term institutions. Every democratic system faces the structural problem of short electoral cycles creating short policy horizons. Integrating sustainability into governance means creating institutional mechanisms that extend the effective planning horizon of democratic governments beyond election cycles. Parliamentary commissioners or ombudsmen for future generations, independent offices with statutory authority to assess the long-term implications of policy decisions and require governments to respond, are being established in a growing number of countries. Wales, Hungary, Finland, and others have created such offices, strengthening their independence, their analytical capacity, and their political authority as an integration of long-term thinking into the institutional fabric of democracy. Sovereign wealth funds that invest for intergenerational benefit. Norway's government pension fund Global is the model. Accumulate and manage national wealth for the long-term benefit of future citizens rather than current consumption. Establishing such funds in resource-rich nations and investing them in sustainable assets creates a constituency for long-term thinking within the financial system. Constitutional entrenchment of sustainability principles, as in Ecuador's rights of nature, Bhutan's gross national happiness framework, or New Zealand's well-being budget approach, embeds long-term values into the foundational legal architecture of the state, making them harder for short-term political majorities to override. Global governance integration. Integrating sustainable governance at the global level means strengthening the international institutions, the UN system, multilateral treaty bodies, international scientific organizations that can coordinate action on planetary-scale problems. Climate, biodiversity, ocean health, and atmospheric chemistry are global commons that no nation can manage alone. Building the governance capacity to manage them collectively is simultaneously building the governance capacity to manage a multi-century, multi-world terraforming project. The most important current integration task is making international climate and environmental governance effective, not just aspirational. This means strengthening enforcement mechanisms, increasing financial flows from wealthy to developing nations for sustainable transition, building the scientific monitoring and attribution systems that make accountability possible, and developing the dispute resolution mechanisms that can address conflicts over global commons management. Science policy integration. The integration of scientific knowledge into policy decision-making, through independent scientific advisory bodies, evidence requirements for major policy decisions, open science platforms that make research accessible to policymakers, is a governance integration task with enormous leverage. Societies that make policy based on evidence outperform those that do not across every dimension of sustainability. Institutionalizing science policy integration means creating standing scientific advisory bodies with genuine independence and authority, reforming public procurement to require evidence-based policy development, investing in science communication infrastructure that translates research findings into policy-relevant knowledge, and building scientific literacy in the population that elects policymakers and holds them accountable. Integrating technological systems. From innovation to integration. The integration of green and sustainable technologies into society requires more than their invention. It requires the development of the supply chains, training systems, financing mechanisms, and social acceptance that allow technologies to deploy at scale. The technology-society interface. Every major technology transition in history, electrification, the automobile, the internet, involved not just the technology itself but the transformation of society around it. Integrating sustainable technologies requires the same comprehensive approach, not just building solar farms and wind turbines, but redesigning urban form around electric mobility, redesigning buildings around integrated energy systems, redesigning supply chains around circular material flows, and redesigning education and training systems around the skills that green technologies require. This societal transformation must be managed actively, not left to market forces alone, because the transition creates winners and losers, and those who lose from the transition will oppose it politically unless their losses are addressed. Just transition policies, retraining programs for fossil fuel workers, economic development investment in coal-dependent communities, social protection for those displaced by automation and decarbonization, are not optional extras to the sustainability integration agenda. They are prerequisites for the political sustainability of the transition itself. Space technology integration. The integration of space technology development into society's broader sustainability agenda creates the direct bridge between Earth's sustainability and planetary capability. Every sustainable technology that has space applications, closed-loop life support, autonomous robotics, materials recycling in extreme environments, remote sensing and monitoring, precision agriculture, should be developed with both Earth and space applications in mind from the outset. NASA's Technology Readiness Level Framework, which tracks the maturity of technologies from initial concept through full operational deployment, should be applied to every sustainability technology with terraforming relevance, with public investment explicitly targeting the advancement of critical technologies through the valley of death between laboratory demonstration and commercial deployment. Space agencies, universities, and private space companies should be formal partners in Earth's sustainability research programs, not separate entities pursuing parallel but disconnected agendas. The International Space Station's closed-loop life support research should directly inform Earthside water recycling and atmospheric management technology. Mars habitat design should directly incorporate Earth's best-controlled environment, agriculture, and circular economy technologies. The integration of space and sustainability technology development accelerates both the cultural and educational integration, building the civilization that can do this. All of the technical, systemic, and institutional integrations described above ultimately depend on a deeper cultural integration, a transformation in how humanity understands its relationship to the natural systems that sustain it and its role as a steward of planetary processes. Education is integration. The integration of sustainability and systems thinking into education from the earliest years is the highest leveraged long-term intervention available. A generation educated to understand ecological systems, circular material flows, long-term consequences, and planetary stewardship is a generation that will design, build, and govern sustainably as a matter of cultural instinct rather than regulatory compliance. This means not just adding environmental content to existing curricula but fundamentally restructuring education around systems thinking, the ability to understand how components interact, how feedback loops create emergent behavior, how interventions in complex systems have unintended consequences. Systems thinking is the cognitive foundation of both sustainability and terraforming, and it is currently almost entirely absent from mainstream education. It also means integrating outdoor education, direct experience of natural systems, and hands-on ecological restoration into education at every level. A generation that has never touched soil, never observed the natural ecosystem, never experienced the living world directly cannot be expected to care about its protection or understand its functions. Direct experience of the natural world builds the emotional foundation on which intellectual understanding and practical commitment rest. Narrative and cultural integration. The deepest integration of all is narrative, the stories a civilization tells itself about who it is, what it values, and where it is going. The dominant narrative of industrial civilization, unlimited growth, mastery of nature, individual consumption as the measure of success, is incompatible with sustainability and with the long-term civilizational project of becoming a multiplanetary species. A new narrative is needed, one that frames humanity not as the conqueror of nature but as its most self-aware expression, not as the consumer of planetary resources but as the steward of planetary systems, not as a species trapped on a single fragile world but as life's leading edge extending its reach across the cosmos. This narrative is already emerging, in the environmental movement, in the overview effect reported by astronauts who see Earth from space, in the growing cultural resonance of planetary thinking. Integrating it into mainstream culture requires its expression through every medium of cultural communication: art, literature, film, music, architecture, urban design, political language, until it becomes the default lens through which people understand their relationship to the world and to the future. The integration roadmap, the sequence that makes everything possible. Bringing all of these integration threads together into a coherent temporal sequence produces the master roadmap from present society to terraforming civilization. The next decade, 2025 to 2035, foundation integration. The critical integrations of this decade are energy and food. The renewable energy transition must reach the point of irreversibility, solar and wind so cheap and widely deployed, grid storage so abundant, and fossil fuel infrastructure so economically stranded that the transition continues regardless of political headwinds. Simultaneously, sustainable food systems, regenerative agriculture, alternative proteins, circular food waste management must reach the scale at which they begin displacing rather than merely supplementing conventional systems. Institutionally, this decade must see the establishment of long-term governance mechanisms in major economies, future generations commissioners, long-term investment frameworks, and carbon pricing systems that begin extending political time horizons. International climate governance must strengthen from aspiration to accountability. The next generation, 2035 to 2065, systems integration. With energy and food transitions underway, the integrations of this generation focus on completing the circular economy, fully deploying urban mining, chemical recycling, and biological nutrient cycling at industrial scale. Biodiversity recovery, enabled by reduced agricultural land footprints, must reach the point where ecosystem services are measurably improving globally. Advanced nuclear and fusion energy development must reach commercial demonstration. In space, this generation sees the establishment of permanent human presence on the Moon and the first sustained crewed missions to Mars. Closed-loop life support, ISRU, and habitat construction technologies are demonstrated at operational scale. The first biological terraforming experiments are deployed in enclosed Martian habitats. The Century Horizon, 2065 to 2125, planetary integration. With circular economies, sustainable food systems, restored biodiversity, and clean energy fully integrated into Earth society, the focus shifts to planetary scale integration, managing Earth's climate actively through carbon drawdown and potentially solar radiation management, deploying biological restoration at continental scale, and beginning the first phase of Martian atmospheric modification. Space infrastructure, permanent Martian settlements, lunar industrial facilities, Space-based solar power demonstrations. Asteroid utilization systems reaches the scale at which the solar system becomes an extension of Earth's resource and energy base. The terraforming of Mars is underway, driven by automated systems and sustained by a civilization that has mastered the art of planetary stewardship at home. The Millennial Vision, 2125 and beyond, multiplanetary integration. The ultimate integration is the emergence of a multiplanetary civilization in which the skills, institutions, values, and technologies developed in the pursuit of Earth sustainability are deployed at multiple worlds simultaneously. A civilization that has integrated green, regenerative, and sustainable systems so thoroughly into its DNA that sustainability is not a policy goal, but a cultural reflex. That civilization is one capable of managing the extraordinary complexity of terraforming, of designing new biospheres, of carrying life to new worlds. The unified vision, what integration actually means. After traversing every domain of systems integration, energy, materials, food, ecology, governance, technology, culture, and education, the deepest truth that emerges is simple and profound. Integration is not adding sustainability to existing systems. It is redesigning systems from the ground up around the principles that sustain life. A society that has genuinely integrated green, regenerative, and sustainable systems is not a society with solar panels on its fossil fuel economy. It is a society whose economy runs on energy flows rather than energy stocks, whose industrial metabolism cycles materials the way an ecosystem cycles nutrients, whose food system builds soil rather than depleting it, whose governance extends its care across generations rather than election cycles, whose culture values complexity and continuity rather than simplicity and consumption. That society, when it looks outward to other worlds, does not see planets to exploit. It sees canvases on which to extend the living complexity it has learned to nurture at home. It does not ask whether it can afford to terraform another world. It asks how the knowledge it has gained in sustaining one world can be applied to making another world flourish. The integration of green, regenerative, and sustainable systems into our society is not a detour from the grand adventure of becoming a spacefaring civilization. It is the adventure. Every solar panel integrated into a community microgrid, every piece of food waste turned into compost, every river restored to health, every child taught to think in systems, all of it is the work of building the civilization that will, one day, carry life to the stars. The cosmos does not wait for a civilization that has failed to sustain itself, but it is infinitely patient with one that is learning how.